Okay, welcome to Kernel Debug Stories. I'm just going to leave it another 30 seconds before kicking off in full, just because I can see the participant count is still climbing, and maybe my clock is 10 seconds fast or something like that. So I will start up in full in maybe even 15 seconds time now, and then we'll kick off. Okay, so just some brief logistics. Normally I include a thing in here about turning your cameras off, but because this is such a big event, we are running this with cameras off by default, so there's no way for you to turn your cameras on. I don't have to tell you that. Questions are very welcome as we go. I've got the chat open, I've got the Q&A box open as we go. I don't always spot the questions coming in, but I do my very best because it sits on a slightly different screen to the one I'm presenting from, but I will try to get to your questions as we go. You will find a link to the slides in the chat, and we have a moderator online as well, Christine, who will answer questions about where the slides are and where you can find things as you need them as we go. Now we're going to kick off with a very quick biography. This is as much as anything so that you can think about my prejudices. Because how you approach debugging is strongly influenced by where you've come from. So I'll just share a little bit about where I've come from so that you can sort of figure out which lessons that I've learned are going to apply to you. So I kicked off my career joining a toolset team when the real-time operating system was typically bundled along with the C library and everything else inside the toolset. So I was a real-time operating system engineer within the toolset team. And as the set-top box industry, which is what ST was involved in at the time, pivoted from custom RTOSes to GNU Linux, I followed along with it. So this would have been about 2001, 2002 maybe. That's when I kind of pivot and start spending some time still on custom RTOS and some time on GNU Linux. During the following years, I worked in almost every bit of set-top box software there is, with the exception of the security coprocessor. So this spans things from networking stacks through to audio video code, not video codecs, but audio video streaming, all the synchronization, timing, and things like that. And from C libraries to software architecture. So a very broad spectrum, which is because I was there for a long time. During my final years, I became a tech lead for a project to replace the driver stack for that set-top box. That was trying to help a very large team of engineers go in the same direction. And at that point, my role became largely consultative. My job was to support and enable team members to make them productive and to solve problems. It wasn't to tackle these things myself. And having spent time in a consultative role, I do prefer to be a bit more hands-on these days. But it did spark interest in things like training and mentoring, which is perhaps how I come to talk to you today. 2014, I joined the Linaro kernel working group. I spent a year working on debug technologies to sit in the kernel. And then I became the tech lead for the support and solutions engineering team at Linaro. I've often been attracted to jobs with breadth rather than depth. Architecture, you can see the breadth of the things I've worked on in the set-top box world, and so that's where I'm at now. I have a job where wide, but not going into absolute domain expertise as some engineers choose to do. What that does mean is everything I still do is nevertheless centered around that background I have in tools and operating systems. So whether I am, leading the support team, whether I'm the training manager at Linaro, whether I'm the upstream KGDB maintainer, all of those things can track back to my heritage in tools and operating systems. So today's training. The way I should put it is the Linux kernel, in addition to things like KGDB, has hundreds of other tools that can be used to help you debug things. Every single one of those tools could be the subject for an hour on its own to explain how to really use that tool. And I've only got 2.5 hours to describe all of those tools. So we have to take an important shortcut. And the shortcut is that I'm going to try and introduce you to the essence of each tool, what the tool is good at debugging, where you would reach for it and why you should use it. I'm not going to go into very much detail about how to use it. I've put as much springboard and other material into the other ideas into the material, so that if you take some of the concepts from the slides, put them into a web search, you should come up with something more interesting to read on the subjects you want to look at. But what I cannot do today is to go into depth on how exactly each tool is used. But we can talk about when you would use it, why you would use it, and the essence of the tool that makes it useful. So we're going to start off with some basics, which is just kind of scene setting and this concept I've called failing early. So the scene setting is thinking about different approaches to debugging. The first type of debugging that most people start to use, and often don't think of it as debugging in some sense, is based on tracing. Tracing is ultimately just the gathering of events during system execution. Good tracing systems have a timestamp which helps you to interpret the information you see, particularly in things like kernel and other things that react to the world around them. And the reason tracing is the first type of debugging that most people meet is because printk is ultimately a low performance form of tracing. It's a free-form text system that, with the addition of timestamping, gives you a certain type of trace capability. Likewise, if you've ever written user-space programs, all the printfs that you litter through your program are ultimately a form of tracing. So despite the fact that tools like ftrace and jump traces and hardware tracers seem exotic, they're actually going back to the very first techniques that you learn to use to debug, to gather events as the system is executing. The second type of debugging tool we might be interested in are profilers. Profilers actually have quite a lot in common with tracing systems, and they're quite often attached to the same trace points. But the difference is they don't provide you with a stream of events. What they provide you is a digest of statistics about system execution. For example, if you have a classic sampling profiler that simply interrupts the CPU quite frequently and tells you what the program counter is, and then graphs, the hot functions by simply they're the ones that are on the CPU most often. That's the sort of thing we can do with a profiler. So they attach to streams of information, quite often from periodic events that simply stop the system and examine it and carry on. We can gather information about system execution. It should be noted that profiles can to some extent be derived from traces. If you have a function call and return trace, you can work out how long you spend in each function. You could use that for profiling if you digested it back into statistics. And then finally, we have the stop the world debugger, which is what I hope is conjured in most people's mind when you first talk about debugging. This is the debugger. Whether it's GDB, Visual Studio, whatever the tool is, its essence is that it stops execution of the machine and allows you to examine the state of the machine. And then in some cases, you're able to continue it. Post-mortem is a special case of stop the world where there is no expectation or intent to restart the world when you're done. So core dumps obviously are traditional post-mortem systems that stop the world and gather information. But in reality, when you stop a kernel, if it is doing useful tasks, it will start to miss deadlines the moment you stop it. And when you restart it, what you'll often see is the recovery process of the kernel as it recovers from a long period where it wasn't working correctly. You can also experience strange things like time doesn't progress quite as you expect because the tick has stopped and other interesting things happen as a result of stopping the world. When I'm doing kernel debugging, it's nice if I can restart the world, but most of the techniques that I rely on don't assume you can step or continue the world at any point and have anything meaningful happen. The techniques I like to rely on are stopping the world, and if I need to examine the state of memory, I can use post-mortem techniques to do that, but otherwise I tend to combine things like tracing and post-mortem together. Something just to plant as a seed in your mind is that post-morteming can be partly automated. An oops trace is ultimately a form of automated stop the world analysis. When you get an oops, the thread jumps into understate base and records the state of the CPU at the point that the fault has happened. And then the oops trace will print out some of the information related to that. The final thing for this just very introductory idea to these concepts is that combinations can be really powerful. The one that's both intuitive and my favorite is combining tracing and stop the world, particularly if you are tracing into memory, for example, and not putting it out to UART, not putting it to screen. Then when you stop in a stop the world debugger, you can gather the trace logs and start reasoning about the history up to the point that the system failed. So the other thing, another concept that I want to bring in right at the beginning is a concept that I've called failing early. So failing early is basically trying to bring the system to, if you're going to do a stop the world style debugging or a post-mortem, the goal would be to bring the system to a halt as soon as possible after the damage has been done, after whatever it is that we don't want to happen has happened. We'd like the system to come to a halt as soon as possible after that. There are a collection of reasons why we want to do that. The first is ultimately that a lot of our trace tools use circular buffers, particularly if you're an embedded system and your kernel messages are not being absorbed by the syslog daemon because there's no disk to put it on, then eventually the kernel demessage buffer gets exhausted and we no longer have it anymore. So where we have circular buffers gathering our information, we have to manage to fail before we evict the evidence that we need to examine the system. The other aspect is that Linux systems are predominantly debugged using self-hosted tools, meaning the tools we use to debug them are themselves running inside the system we're trying to debug. And bugs will damage the system. So if bugs damage the system and you allow the system to continue running, it is not necessarily going to be the case that the tools that you want to examine the system are going to still be capable of being run if we've allowed a lot of damage to accumulate. So the faster we can fail, the more hopeful we can be that we haven't done any kind of corruption that prevents our self-hosted debug tools from working correctly. And the final thing is the symptom may be a second order effect. And the faster we can bring the system to a halt after the second order effect is observed, the more likely we are to be able to go backwards through the logs and try and figure out what the first order effect that actually provoked the cascaded failure is. And then there is a very simple pragmatic reason that if you do certain types of particularly traces, if you're doing a function graph trace, then the volume of trace data is very, very large. And without some mechanism to fail early to detect when something bad has happened, then it's really hard to find which bit of the trace data you need to go and read. You know, most often when you have a bug, if you failed shortly after the bug manifests itself, then you're only trying to look at 10 milliseconds maybe of trace data. It does depend on the nature of the bug, the window, but a very small window. So you might have captured many minutes of trace data, and there's only this tiny 10 millisecond window that you actually care about. So finding when that happens by having something wave a flag and say this has not worked correctly really does help you navigate these big trace logs. So Linux does include a large number of debugging tools that will automate the process of failing early. We shall talk about a number of these in a minute. Most of the automatic tools that are present in the kernel will report failures via printk. Printk is very defensively coded. It is difficult to damage the kernel to the point that printk doesn't work. It is not impossible, but it is difficult to damage the kernel to the point that printk doesn't work. The obvious exception is bus lockups. We'll be talking about bus lockups towards the end of today. But if your CPU is still running, a bus lockup ultimately works by preventing a CPU from making forward progress. If your CPU is running, then it's a very good chance that printk will be functional if you call it. So while we're talking about failing early, we can bring in this whole arsenal of automatic tools built into Linux to help us find problems. Okay, so I've just got a bridge for while we're going back onto failing early. Stop the world. So by stop the world, I'm describing the model with which a classic debugger works. So things like tools like GDB or the Visual Studio debugger, if you've got the clicky interface, or Visual Studio Code. Any of these tools that allow you to stop the target, step, look at some variables, step a few more and continue is an example of a classic stop the world debugger. And what I mean by stop the world is that in order to examine the system, we stop the process or the system from making forward progress so that we can go and examine it. There are types of debuggers that actually allow you to run live and to read out memory from live systems. They don't fit into the taxonomy, I guess. So debug tools can be quite exotic. There are debug tools that do not fit into this taxonomy that I've offered here. But you don't need any special hardware to stop the world. You usually do it with traps in software. So a breakpoint, for example, is basically a instruction the CPU doesn't know how to execute. It causes the trap handlers to run. And by running trap handlers, we gain an interruption to the underlying process. We can then stop all the other threads in the process. We can then trap into GDB and GDB can go and read it. We can have similar things in the kernel. When we take a breakpoint in the kernel, we can move into this little monitor that allows us to interact with the target via the serial port, for example. So coming back to failing early, while we could use the automatic tools, and we should use the automatic tools if they're available, it doesn't mean that if we can't find an appropriate Linux debugging tool that we give up on the concept of failing early, because we could be starting to look for ways to recognize the signature of our bug in code. So in other words, if you've got a bug that you're examining and you can see that it has this effect on the system, maybe this variable gets damaged or something changes that you weren't expecting. One of the things you can do is you can simply write a piece of code that tries to recognize if the problem has already happened. And then you can sprinkle your recognizer over the kernel, and that gives you two very useful pieces of information. The first is that at this point, the system was healthy. And the second is at this point in time, the system has failed. And that gives you your window that you're interested in tracing to find out what's going on. So although you can use lots of debug tools to find faults, you can also write fragments of code yourself to try and recognize the signatures and problems that you have associated with these things. And that can help you reason about when the system is damaged, how, and so on. So let's look at some of the kernel's built-in fail early concepts. So I'm not able to give you an exhaustive view of all the failing early techniques because there are an enormous number of them. I'm just going to show you a few of the common areas, stack, memory debug, lock debugging, and so on. If you want to go deeper, go and look at the kernel hacking menu in the Linux kernel config system. So first off, stack overflow detection. This is a common thing we want to do to make sure the stack has not overflowed. Debugging stack overflows is tremendously difficult, especially on 32-bit ARM systems. And so we want to make sure that the kernel stack does not get overflowed. Kernel stacks are actually very small as well. They're between 4 and 8K. If you allocate big arrays on the stack, your system will fail. So there are techniques that we can apply to try and spot when we have problems with stack overflow. The simplest is frame warn. This is actually a static checker. It's simply, when you're compiling, it will issue a warning to say this function has a stack frame that's larger than this many bytes, classically a K. So if you've made mistakes, then it's run quite frequently on the standard kernel, but particularly if you've got vendor kernel from SOC vendors and you're concerned that there might be some things in it, turning frame warn on and checking that we haven't got excessively large stack frames in those new pieces of the kernel can be very useful. Once we've done some basic static checks to look for obvious problems, we can now look for problems at runtime. So the other two mechanisms here are designed to find problems at runtime. So the first one, shed stack end check, basically attaches itself to the code that happens when a task is taken off the CPU. So when a task is stopped from running because it's either gone to sleep or because, excuse me, because it's gone to sleep or because something's preempted it. We can check to see if the stack has ever overrun its value. So this doesn't give us an immediate stop. This is effectively looking at a second order effect. But nevertheless, we can find out which task has gone wrong. And at that point, we can start to instrument it or try and figure out what it was running and get us closer to the actual place where we overrun the stack. The other thing we can use if we've got 64-bit systems is something called VMAP stack. VMAP stack effectively allows us to use the MMU to spot if we overrun the end of a stack. And the great thing about that is it will stop and give us a stack trace at the exact moment the stack overflows. So that's a really powerful technique, and by turning it on, you don't just get the stack check, you also know the stack hasn't overflowed, which makes a lot of other reasoning about what might have gone wrong easier. So vmem stack is highly recommended if you're concerned about any kind of stack overflow. Moving on from that, we have more general memory debugging, where we're trying to think about whether allocators are being used correctly, whether we're writing past the ends of dynamically allocated memory and things of that nature. There's a couple of examples up here. So I'll bring up slub debug. Slub is the standard allocator that we use to allocate slabs. And this is basically decomposed pages where we might want to allocate small blocks. It is almost always present. So slub debug does have a config option that allows you to turn it off. But when slub was introduced, that option didn't exist. The debugging was there by default. The only reason slub debug came in was to allow slub to tackle some very, very low code size environments, almost to the level of, not quite to the level of microcontrollers, but that kind of size, very, very, very small Linux systems. If you're in anything bigger than that, there's simply no reason really to turn slub debug off. Because it only really affects code size rather than performance. And it does give you access to a number of tools. So at boot time, you can put this slub debug equals argument on your command line and command what you want to do. So you can do things like look for abuse, you can look for double free, you can track who's allocating memory so you can chase down leaks. You can turn on something called poisoning. Poisoning is very, very simple. It's basically when a block is deallocated, you fill it with a poison pattern. When it's reallocated to somebody else, you check the poison pattern, verify that it hasn't changed. This will help you spot writes after free. You can also poison with undefined values. So if you've got a memory allocator that gives you memory in an undefined state, you can actually poison it with undefined values so that you can spot if, for example, pointers are followed in the wrong direction and so on. Moving on from that, that's basically a classic heap allocator, really, and it's got all the features you would expect of a heap debugger to provide you. We can then move on to things like debug page alloc. So debug page alloc is very similar to vmap stack. It basically changes the way the physical memory is mapped by the kernel. Normally, the kernel uses something called big pages, which reduces pressure on the fault handling system by giving you sort of 2 megabytes at a time in each page. The effectively enlarges the TLB in the MMU. So what we can do instead is, instead of having the kernel mapped to these big 2 megabyte pages that are nice and efficient, it switches down and maps them as 4K pages. This, like I say, this does cause more frequent faulting when you're doing certain kernel code, but in exchange for it, it means we can enable and disable access to particular pages. So debug page alloc basically says that if memory is free, it will not be mappable in the kernel. The kernel will not be able to read and write to it. So if you do a use after free, if you read past the end of an address, etc., and you hit something that's unallocated, you'll get an immediate fault as you've gone past. So that's a very powerful way to make sure that free pages cannot be addressed by the kernel. Page poisoning is an alternative mechanism to try and spot use after free in the page system based on poison patterns. So when you free pages, instead of taking off the MMU, we can fill them with poison patterns, and then we can validate when we reallocate. It is less powerful than debug page alloc, but for a start, it will run on 32-bit ARMs, which you can't run debug page alloc on. And it has different performance characteristics. So it has, you know, good upsides and downsides, but we have a variety of techniques to do memory debugging. The other big area that comes up quite a lot is lock debugging. So over the last 20 or so years, the kernel has been on a journey towards finer and finer grain locking. As we get bigger and bigger and more complex SMP systems, the kernel needs finer and finer grain locking to make sure that all the CPUs get to do their thing. The locking patterns in the modern Linux kernel are sufficiently complicated that most of the time, most programmers don't need or want to think about exactly how all the locks interact. There are so many of them. Eventually, if we need to debug fully, we do have to eventually reach about all of them. But most of the time, we only worry about our local locks, and we hope that everything else is working as it should. So there are various things we can do to study in more detail. Debug mutexes is a relatively minor thing. It's not as powerful as the name implies. The mutex API has a couple of constraints that beginners are unaware of. So this is basically a safety net for beginners. So for example, it's absolutely forbidden to take a mutex in one thread and release it in another thread, because that's not what mutexes are designed for. That's not a form of communication we want to be using mutexes for. If you want to do that, use a semaphore or a wait queue. So this one is very much there to give you a safety net for beginners. It can also spot problems in other places. The others get rather more aggressive. So things like debug atomic sleep is very, very important and one of the most useful checks. It's there to make sure that you never accidentally call a sleeping lock whilst you are running an execution context where it is not safe to take a sleeping lock. So classic examples of this are when you're running an interrupt handler, when you've got interrupts locked, and I think when you've got preemption locked as well. So these are basically things where you're in some kind of critical section where it is unsafe. When you own mutexes, of course. Sorry, when you own spin locks, you are also not permitted to take to do sleeping locks. So this will pick up certain types of sleeping locks like mutexes being used inappropriately. There's a custom memory allocator, just to show that these things do interact somewhat. One of the nastier things to have to do in debugging locks is if you have got some component that is using a lock that has been freed. Sometimes you'll find it through poisoning. You know, if you've poisoned things when you free it, then when you free the lock, all the pointers will break, and when you follow the pointers in the lock, we'll see distinctive patterns in the stack trace. But overall, deallocating locks while they're in use, it does create a number of problems. So debug lock alloc is a mechanism to detect when a lock has been used after it's freed or other abuses of the allocation process for locks. So it's technically a specialized memory debugger, but it applies to locks as well. And then we have a couple of other things like the lockup detector that uses a timer IRQ to verify that the scheduler is working correctly. So basically, it's a periodic timer that looks at the scheduler and makes sure that it's correctly scheduling tasks. And on non-ARM platforms, there is also, if you have a non-maskable interrupt, you can use periodic non-maskable interrupts to verify that the interrupt system is working correctly. Now, there are some Azure tree patches developed by somebody on my team, in part, I think, that can allow you to use on ARM 64-bit systems the pseudo NMI for this kind of purpose. But they're not in the upstream kernel as things stand. And then finally, RCU stall detection is not really a debugging technique in itself. It's a useful property. So when you're in an SMP system, quite often one CPU will jam on maybe a spin lock that can never be satisfied, and the other CPUs end up eventually stuck waiting for it. But one of the things that can happen is they end up trying to do a read copy update rendezvous. So read copy update is a mechanism for optimizing read intensive data structures. It basically means that most people just read it with no logging at all. If you want to modify it, you read it and make a copy. You then update the copy, and then eventually you switch over to the master copy of the data structure. And to do that, you have to rendezvous with the other CPUs at a point when you know that you're not in any of these read sequences. Ultimately, if something wants to rendezvous and it doesn't get the opportunity to do so, then it will issue a stall detection. It's saying that this other CPU has never attempted to do a read copy update, finalize a read copy update. It doesn't tell you what's gone wrong with the other CPU, but it's almost always a signature. If you get an RCU stall detect, it's almost always going to be that one of the other CPUs in the system has stopped working. That does not apply to Big Iron. If you're into the kind of 128 core server end of the world, RCU stall detection can happen when just things are really, really busy and there's intensive use of locking across the various cores for different reasons. But on small embedded systems, when you've got 4 or 8 cores, RCU stall detection is almost always because one of the cores has failed. So if you see it, it doesn't get you a lot way forward, but it allows you to start then working out what do I need to turn on to try and find this deadlock that we've got. Okay, the thing we have to discuss when we're talking about levels of intrusion is, sorry, when you're talking about failing early, is the intrusiveness of the tool. So by having intrusive tools, we can build very powerful tools that can spot very complicated errors and report ones that humans would be finding it quite difficult to track. The problem is that because they are powerful and doing lots of housekeeping, they will also slow down the system and cause trouble for it. Two of the major problems are that if we consume these resources, we might alter the way the bug reproduces. The more resources we use, the slower we do the timing. We miss timing windows, various things. It's even possible to have bugs that simply will not reproduce on an instrumented system, but do reproduce in production. Those are typically called Heisenberg bugs. They are frustrating. Ultimately, when you find them, you end up having to scale back your instrumentation and come up with clever ways to make the instrumentation less costly, just to try and have a little bit of observation on when they're being reproduced. There's not many shortcuts. When you're faced with a Heisenberg bug, failing early, you might start using custom detectors and other mechanisms that are lower overhead and guarantee you can still reproduce things. The other thing that comes up with intrusiveness, particularly on low resource embedded systems, is it not being possible to run the tool at all. If you have tools with heavy memory overheads or that cause the system to run so slow it cannot meet its primary mission, then there's only so much we can do to mitigate that. One thing we can do, however, if you've got a low resource embedded system and we want to deploy a tool to check certain parts of the kernel that we're concerned about, we have done some preliminary triage. We think this is the system that's not working as it should, and we'd now like to run some automated debugging tools over it. We can work on a partly integrated system. So we could run maybe subsystem or unit tests with the other part of the system not running to free up the resources we need to make it possible to run the tool. Just some examples of some sort of useful but expensive tools. Poisoning in all its various forms is a useful technique. It's actually relatively cheap, except when you're allocating. So it has a very uneven cost. When you're doing allocation intensive workloads, you're allocating or deallocating lots of pages, poisoning can become quite expensive. If it's only happening on particular pools or with particular workloads, you won't see much cost to it. So it's a variable thing, but it can be expensive. And then we have a couple of things that genuinely are quite expensive. We have things like prove locking, which we'll talk about in a moment, which is a mechanism to try and spot potential deadlocks without having to reproduce the actual deadlock. We have kernel address-based sanitizer, which instruments all memory accesses and allows you to do validity checks against a bitmap to find out if you're allowed to read or write from a particular byte. Now, naturally, adding software that runs on every single memory access to determine if it's safe to read and write to the memory is an expensive operation. There's no two ways about it. In this case, we end up using 1/8 of available memory simply to manage the validity structure. The heaps will become less RAM efficient because they have to leave spaces to have invalid gaps between all the allocations. And with the instrumentation, the kernel ends up running about 3 times slower than we normally would. So it's a big cost running kernel address-based sanitizer, but it will tickle out things that would be very difficult to discover by other means. One of the nice things we have on ARM platforms is the hardware-assisted address-based sanitizer. Sorry, address sanitizer. It's not address-based. Address sanitizer. Basically, it's looking for invalid memory addresses. Hardware assisting we will talk about in a moment, so I will talk about it there. So the reason I'm putting these ones up, I would just like to talk a little bit about some of our most sophisticated tools we have in the kernel. So just make you realize how much work some people have put in to trying to make the kernel as bug-free as possible. And to kind of, really illustrate just how far you can go with these kind of fail early kind of concepts. So in the left-hand side here, I have 2 threads, which if they occur in exactly these timings will deadlock. So I've only shown the lock operations. You can assume there's lots of other code between the taking of locks and the freeing of locks and everything else. But the first thread takes a subsystem lock and then takes a driver lock. And I've picked these names very deliberately because this is a very common mistake to accidentally, in your when the system interacts via the subsystem, what will happen is subsystem will take some locks, the subsystem will then call into a driver helper, the driver takes a lock, and then it does the action. That's absolutely fine. But then quite commonly in some kind of interrupt handler, the driver interrupt fires first, the driver takes its own driver lock and then calls a subsystem helper, not realizing the subsystem helper is also going to take the subsystem lock. That creates this window for deadlock. It's called a deadly embrace. And the timing window to reproduce the deadlock can be very, very small. It's a difficult thing to find during subsystem testing. It's the kind of bug that we might envisage being discovered in final QA or in the field. And at that point, most of your tools to help you work with it will be difficult to deploy or diagnose. So prove locking is a mechanism that allows us to surface that bug much more easily. It can even find the bug when you're running on a single thread rather than multiple threads, because it's always wrong to have one lock sequence one way around and one lock sequence the other way around. Almost always wrong. There are a few cases during things like startup where you might get away with these things. You can have theoretical deadlocks that are not reachable in the real world, but overall, rather than reproduce the deadlock by causing this stuff to happen simultaneously on two CPU threads, we can have one SMP core that is, so incidentally, when I'm talking about threads here, these really mean hardware threads rather than operating system threads. We can be running a one SMP core and we end up seeing a lock subsystem log driver, and we can remember that lock sequence. We can remember that the subsystem was locked first and the driver was locked second. We can then see the opposite thing on the same thread. We can see lock driver, lock subsystem, and we can also remember that lock sequence. And we can then compare it to all the other lock sequences we've ever observed. And we can say that there is a contradiction here because there is a risk of deadly embrace between this type of thread here. So what happen when we have prove locking enabled is we no longer have to hit the timing window to show the deadlock exists. We simply need to turn it on, run some representative workloads. That means you're exercising all the different code paths. And as you exercise the code paths, it will automatically be checking to make sure that this type of deadly embrace can't happen. So it's a really powerful technique. It does have lots of costs because remembering the lock sequence is expensive, and then comparing all the lock sequences gives you slightly lumpy behavior because every time you see a new lock sequence, we have to go and check again. I haven't got any figures for how much that costs, incidentally, but it does weigh things down if you're running lock-intensive workloads. So let's talk about this hardware-assisted address sanitizer. So this is looking for memory management problems, and the reason we bring it up here is because it relies on a fairly unusual ARM feature called top byte ignore. Top byte ignore basically says that the 64-bit access made by the CPU is actually a 56-bit address and a top byte that we're going to ignore, that we're not going to care about when we turn it into a pointer, which means we can put any value in there. It's an 8-bit tag that we can use for any purpose. It gets used for a couple of things. So Apple phones, I believe, use the tag to optimize certain types of allocation to make the heat more efficient. But in Linux, it's mostly used for debug techniques. In user space, again, you can use these tags in user space to implement features. In the kernel, it's used for debugging. So in the kernel, we can turn on this feature. We get the top byte ignore. And when an allocation is made, it is given essentially a random tag, which means the pointer embeds the tag. And every time we get memory access, we go and look at a shadow data structure to find out what tag that address is supposed to have. And this is fantastic because if you overrun the buffer, then the shadow description will have a different tag at the point you overrun with a 1, 2, 3, 6 possibility of a mismatch. But generally speaking, two bordering blocks of memory that should be accessed through different pointers will have different tags. And so if you access them through the wrong pointer, i.e. you overflow, then you get and trigger an error. Even better, we can track almost all use after free bugs, because when the memory gets reused with a new pointer, it will have a new tag. And the result of that is without having to maintain any old state, we can just free and allocate as normal But if we take an old pointer and access it, the tag will mismatch and we'll be told about that as well. So most of the common memory management mistakes that you can make will be caught using the hardware-assisted address space sanitizer. So it's a very powerful thing. It does have significant overhead. It's similar overhead to the address space sanitizer, about 3x cost in kernel code. That is just in kernel code. Obviously, it doesn't affect the performance of user space, but it gets really powerful, really capable. If you are lucky enough to be working on an ARM system with either ARM v8.5 or v9 CPUs, they're on their way. They're not very common at the moment. There is even something called the ARM memory tagging extension, which brings in a lot of these shadow capabilities and makes it possible to use hardware to check the tag for you. It becomes a 4-bit tag then rather than an 8-bit tag. So it's not quite as precise as the hardware-assisted version. Sorry, the hardware-assisted version with less hardware deployed. But in exchange for that, the overheads are much, much lower. We still need overhead. We still have a tag to make. We still have to maintain the tag memory. But because we can use hardware opcodes to accelerate the various checks that we're going to do, it becomes a much, much more plausible thing. The downgrading performance is much, much, much lower, and the memory overhead is less. And then finally, while we're talking about failing early, this is just something I thought was interesting because it brings together some of the ideas from profilers of periodic checking and stochastic analysis with failing early. So Kfence is another memory debugger technology. And unlike things like LockDep, it is not designed to find all the bugs every time it runs. It uses the same technique as a user space memory book debugger from the 80s called Electric Fence, which is basically to allocate a block of memory and arrange for there to be an unused page after the block of memory, so that if you go past the edge of the end of the block, you'll get an MMU error. That was a very powerful technique. It was a very neat and effective technique when it was introduced, but it does have quite a significant memory overhead, because it means every allocation, no matter how small, will require at least 4K of RAM and 8K of address space. Kfence is designed to be used in production. It's designed to be used in production system and have essentially an almost undetectable amount of reduction in performance. And it does this simply by not instrumenting all memory accesses. Sorry, all memory allocations. I should say allocations. Kfence works by intercepting allocations and arranging for there to be a free page at the end of it. So it works by not instrumenting all allocations. It basically has a timer. It will allocate as normal until the timer expires. And then if there is enough space available, it will make the next allocation into an instrumented allocation. And the idea is that if you run enough systems with the same kernel and there was a bug in it related to memory management, it's not that you can guarantee to reproduce it on any specific system, but through the collection of OOPS traces and everything else, from your fleet of machines, you would still get evidence that you've got mistakes. It is obviously only suitable for situations where crashing is not a mission critical problem. And of course, if you've got failovers against servers, then you have those kind of properties because you just fail over to another server while the other one reboots. And it means that you can find certain types of bugs, particularly if you want to chase down memory allocation. Memory mismanagement is a good place to look for security bugs. So turning this on in your whole fleet is, even though it makes them crash slightly more often, might still be a very valid thing to do. Okay, so that was failing early. And we're now going to move on to what we've called the stories. So the stories are basically, they're not really use cases. I'll pull one up so you can see. They're slightly more abstract. Use cases are normally quite concrete and are designed to help you figure out the requirements in a software architecture most often. The stories here are describing an idea of what you want to do, and they're deliberately slightly vague. And the reason they're slightly vague is because I can then introduce tools to address the different vagaries. It's basically a route by which I can bring lots of tools to your attention while giving you a sort of thought of what you might be using it for. So the first story is called I Can't Reproduce, but my customer can. And it's characterized by this, that you've run it on your desk and it's running fine. You've delivered the system to your customer and they keep seeing this odd behavior, this weird thing. We don't have, it's not easy for us to reproduce it locally. It might be because we don't have the equipment. It might be because they won't give us the software. It might be because they have a bank of 400 machines and we've only got one. That's quite common at Linaro. And so we simply can't get the machine time up to try and reproduce. We've got on site lots of times already, or it's COVID and you can't travel. So we want to try and manage the problem and try and fix the problem remotely without going to the customer site and actually feeling the problem. So the scope for this particular story, odd behavior, we've not defined what that means. It could be any of the problems we've discussed today: memory corruption, Stack Overflow, deadlock. We haven't really gone into any particular details about what odd behavior means. The level of skill of our customer may be different from our own. This doesn't mean that the customer doesn't know what they're doing. It's more that in your case, you're probably the driver specialist doing the kernel and they're probably an application developer, or they're a systems integrator. You know, they will not be as familiar with the chip that you've been working on or anything else. So we might have to accommodate providing instructions to the customer while being confident that when they run an experiment, we can be sure that they've run the experiment we intended, rather than an accidentally different experiment. It is implied in this that the customer is probably external to the company. It doesn't have to be, but for internal customers, where you can sit the same side of a firewall, then telepresence technologies like VNC that allow you both to type simultaneously while chatting on a headset and seeing each other's screens can be more effective than doing true memory development. You know, the actual fact that you can watch somebody work and then say, sorry, can I try typing a few commands, is a good way to do a joint investigation. Obviously, you can use video conferencing tools or some of the what's it called, Teammate, to share presence across firewall boundaries. But generally speaking, and we're bringing this in because we can't do some kind of buddy system. They might be in a different time zone. There's lots of reasons we might do remote development, but in this case, we're assuming that we can't fire up telepresence. So the consequences of this are inevitably that debug cycles will take longer than usual. Long debug cycles means that you have slightly longer to think about what experiments you want to run. It's no longer an interactive compile debug cycle. It's now a think hard, gather some ideas of what might be going wrong, work out how to act on those ideas, and then work on things. So we'll have these nice long debug cycles. Deployment of the debug tools. It's not, I don't really like talking down to the customer in this case. It's not what I mean. It is the fact that we're going to provide instructions and we need to be confident that when the customer sends us the results back, they have run the experiment correctly. And obviously, when they give us the results, we have to be able to exfiltrate those results back to our desks for analysis. So those are the consequences of this type of problem. And I think one of the most important tools that you have to be skillful at to make this kind of I can't reproduce but my customer can system work is source navigation. Let me step one of the other reason I put this story first, by the way, is that this describes the experience of most Linux maintainers. You know, I, as well as KDB, I'm also involved in maintaining backlight. I have some devices with a backlight, but there are some 30, 40 odd backlight drivers, and I only own 2 or 3 of them. There's no way I can reproduce all the odd behaviors that you could ever see on a backlight. So the other aspect of this, I can't reproduce my customer can. This is what will be happening if you are reporting things to maintainers. They will be in the position of asking and suggesting ideas of how you can fix things, or reviewing code and trying to work out what it's fixing when they can't reproduce it. So these ideas that you can't reproduce things is actually very common for Linux maintainers. So back to source navigation. Source navigation is particularly important for remote diagnosis. I mean, it's important all the time for making you more productive as a programmer, but it is especially important for remote development, because the cycle that we have is quite often we will receive maybe a D-message buffer from the customer or a log of the UART saying, this has happened, what's gone wrong? And you read it and you find a couple of error messages, and you're not entirely clear what has caused those error messages to manifest themselves. So the job then is to take those error messages, study the kernel code, and create some theories about the different ways that code could go wrong. Once you've got your theories about the different way the code could go wrong, then we can perhaps get rid of a few. If we can find print Ks in some of the code paths and they are not in the log from the customer, we can cross those out. So you just by using the source navigation and without doing a round trip, we can say, well, the problem's not this, the problem's not this. There are now some examples of what might be going wrong, but we can prune the options by careful source navigation. And to do that, that implies that you have one or more indexing tools well integrated into your workflow. The truthful statement is I don't care what indexing tool you use. There are many available. On the slide right now is a same default that happens to be the one that I use. So this same default is based on typing make cscope into the kernel build system. And that will cause the kernel to index all the architecture files, the drivers, and the kernel core source. It will not index the other architectures. So one of the things that you do observe from time to time is you say, I wonder how spinlock works. You go into spinlock, and it will give you all 13 implementations from the 13 architectures, which is useful if you're trying to work out if your code is portable. But it's not so useful if you're trying to debug. You really would prefer to know exactly how the spinlock works on your platform. So there are other similar targets in the base. There is make ctags and there is make global for GNU Global, which is another source navigator. You don't have to copy me, but that's the same default if you haven't got a reason to pick something else. So make cscope will index the source code. You then usually got editor integration that can pick up the cscope navigation and study things. If you haven't got editor integration, there is actually a tool called cbrowser, which is enormously old-fashioned. It's still written in Tickle TK. It's not as easy to run as it used to, so editor integration is definitely the preferred approach. And one final detail, if you are using a source navigator that makes it difficult to find structure definitions, then you can use the git grep to hunt structure definitions. The reason this comes up is the kernel is well known for not using type defs very much. If you've got a struct foo pointer in a function argument, it would usually be introduced as struct foo star. The thing about a struct foo pointer is you know how big it is because pointers are always the same size. So you don't have to define struct foo before you use struct foo pointers in header files. What you have when a struct foo appears in a header file and it's not been used previously is a declaration of the structure foo, but not the definition of the structure foo. And some source navigators, when you try to ask it to show you the declaration or to show you struct foo, doesn't show you the struct foo definition. It shows you all the places where struct foo is declared, which means you can quite have hundreds of source files and you're trying to find struct foo in a search of hundreds of header files. It is much, much easier. If you have a source nav that gives you too many answers when you ask it what a structure looks like, is to use this git grep, or switch to a different source navigator that doesn't have that problem. Finally, I did mention that we were going back and forth between printk and the source navigator to reason about our system. So the first thing that happens when we see something odd in the dmessage buffer is we've got to find out where it came from. And we don't always know where messages have come from. So classically, messages that come out of the kernel will have a timestamp if it's been enabled. It will have a tag of some sort, and then it will have a message. In this case, found 10 widgets. I convert that when I want to search for that into a much smaller string. Obviously, I can't search for the timestamp because that differs each time. But additionally, XYZ is usually either a device name or a driver name. And in both cases, it does not appear in the source code. So it's not something we can grep for. The grep that we want to do is going to be based on just this message because it will appear in the source code. In this case, I've guessed which ones are variables and which ones are fixed strings, and I can search for found wildcard widgets. And that has a good chance of showing me the places in the kernel that could emit that type of message. So by a combination of stripping off the tags, finding the unique parts of the message and then getting rid of the variables by wildcarding them, you've got a very good shot at finding exactly where in the source a message that you find in the print K buffer has come from. The print K buffer is also vitally important when you're doing remote debug. And the reason that it's easy to use, it's robust, and it's almost always on. And that means that the messages you get back from your customer are always going to be reliable. You can check them. If you get the print K buffer from the dawn of time, you can check that they've put the correct version of the kernel in. So if you send them a kernel to run an experiment, always get them to send the whole logs, because the first thing I do when anybody sends me logs is I go and check that the version of the kernel they've run the experiment on is the one I was expecting them to run it on. It's quite common when you've got bootloaders of different types of embedded systems that people accidentally run the wrong kernel. You have to check for these things. So the classic remote diagnostic loop with print K is that you study the existing log buffer. You then, as I say, you use the source navigator to form a collection of theories about what might have happened. And then you can go through and create an alternative kernel with enriched log messages to prove and disprove each theory. You could even use tools like trace points, what they call K-probe based trace points, dynamic trace points, to run this on a live kernel if you wanted. But in the case of embedded systems, you quite have to send them a new kernel. It's easy enough. So you share the kernel, you cycle around, and you slowly hone in on exactly what has gone wrong. That's an excellent working practice because it's very easy for our customer to work with it. It's a technology they'll understand. There's no effort for them to understand how it works. The problem with it, if it is a problem, it's just a consequence really, but on embedded systems with a UART-based console, then the performance of print K can be very bad indeed. This is being worked on, and in the last couple of kernels, there has been a lot of work to refactor print K and change the way some of these messages are handled. But certainly if you've got a kernel that's a couple of versions old, this will be how it works. And the thing is, when you do a print K and you go to the console handler and it's pushing out to the UART, the CPU just spins while it's waiting for the UART. So in other words, if you output half a line of text, 40 characters at 115200 baud, that will take about 3 milliseconds. Your CPU will be doing nothing else for those 3 milliseconds except waiting for the UART. That means that heavy logging to the console is one of the most intrusive things you can do, which means it is quite common to get Heisenbugs. As you add kernel logging, it's not uncommon for either the Heisenbug to go away, the bug to go away, or for the system to fail because you have too many things going on. So the obvious thing you can do to resolve that is to turn off the console, and then you won't issue things to the UART. If you don't issue things to UART, it becomes much cheaper. Then of course you have to have a different way to extract the buffer, but if you can use dmessage or something like that, you have the option to do it. As mentioned, the current kernel is going through a refactoring that makes print K modal essentially. So when you print to the UART from user space, we don't have the CPU spinning around doing nothing. When you print to the UART from user space, it goes into a larger buffer. The buffer gets dequeued from an interrupt handler, and the message goes out delayed from when you issued it. That's where the kernel is moving towards. But then, if you do that, then you have this problem that when the kernel is panicking, or when there are big problems with the kernel, you don't get to see the output from the UART because we panic before we've dequeued the buffer. So there is work going on to try and recognize these two cases. So when the system starts to fail, it starts using directly using the console as it did before. But when the system looks like it is alive, when it's surviving, it's trying to avoid these spinning waves. But nevertheless, if you want to, certainly if you're running an older kernel that hasn't got these features implemented yet, disabling the console is the simplest way to avoid these costs. They will just go into the print K buffer, the dmessage buffer. They won't end up costing us output. The other aspect I think it's worth bringing up is to understand dev debug and PR debug and how they work. So dev debug and PR debug allow debug style messages to be left in the kernel. The odd thing about them is they are disabled by default. And by disabled by default, I mean they aren't compiled in, they cost nothing, they don't do anything. They are no ops. There are two ways to make them active. One of them is to hash define debug in the compilation unit you're using, and that will cause those dev debugs and PR debugs to convert into normal print case that output at kern debug log level. A better technique might be to use something like dynamic debug, which allows you to add, it enables all the debug. So if you enable dynamic debug, all the debug messages get turned on, but they are suppressed by default, and they're using a relatively efficient switch so that the cost is low. By turning on dynamic debug just across the board, you can add lots of very rich log messages for every debug cycle. You can even have multiple experiments where you say, okay, so turn this on, which is going to give me lots and lots of information, but it might cause highs and bugs, or it might cause the system not to work. So you can also run with these combinations of kernel command lines to subset the different experiments. You can run multiple experiments with the same kernel binary, which again allows you to cycle through with your customer more quickly. Note that disable by default is not the same as the log level. So they are genuinely disabled by default. They are not compiled in. When they are enabled, they will output at log level 8, which goes into the dmessage buffer, but it doesn't go to the console log by default. The default console log is 7. If you're not quiet and you're not debug, then the default console log is 7, which means it won't go to the UART by default, which is quite often a good thing. If you want to turn on lots of debug information and the system hasn't crashed, it's much better just to use dev debug, PR debug to log everything and then extract it from the dmessage buffer without worrying about the UART. So that's quite a lot of information about a tool that everybody's probably already been using. But yes, recognizing the performance costs and making sure that we use dev debug to maximum advantage. Dynamic debug is a nice, powerful tool. I've introduced it in the lab sessions for today's talk. It's definitely worth exploring and making sure you use it when it's a tool that fits, when it's a good tool to work with. Other tools we could bring to bear on this problem. We can't reproduce, our customer can. Debug.fs can be an interesting one. So Debug.fs, together with some of the other virtual file systems, can be used to gather information about the system. Very easy to write a shell script that snapshots your own system and then test the snapshot and then get the customer to snapshot their own system and compare them. So we can look at things like regulator state, clock state, things like that. There's different subsystems that present different information in Debug.fs. The best way you can get a sense of what is available is to fire up one of your embedded systems, mount Debug.fs, and have a look in it. There is one thing I would like to particularly mention about RegMap. So RegMap is a tool to abstract register accesses to some extent. So RegMap allows you to have things like memory mapped IO and 2 different versions of it where the registers aren't laid out exactly the same way in memory. It also allows you to abstract things like the physical media, like low-speed sensors are quite often hybrids of SPI and I2C, and depending on how you talk to the peripheral, depends how it talks back to you. So the driver knows how to read and write to registers, and then RegMap knows whether you're connected to that particular peripheral using SPI or you've connected to that peripheral using I2C. Either way, one of the great features about RegMap is if you have RegMap on your system, and your driver is using RegMap, then the register set that you are working with is accessible to user space in Debug.fs. In other words, you can ask your customer to collect the register state of your driver and compare that to that of a working driver and see if you can get any clues about why the driver stopped working. It's not always as profitable as PrintK, but where you have RegMap, your PrintK is always there. It's always going to apply. Debug.fs will depend on the situation. And just as a cute thing you can do, try git grep for this string. RegMap doesn't just allow you to read the register state. There is some code in the kernel that allows you to poke registers as well. So for example, you could write a shell script that pokes the reset flag in a particular peripheral. Again, it allows your customer to run an experiment. The reason you're grepping for this is because this is considered such a debug feature that it doesn't have a config option. You can only turn it on by physically reaching into the source code and enabling it, but the code is there. So if you want to poke registers from DebugFS, you have that capability. It's also great for driver writing. I mean, even it's a great feature. The writing to registers is such a great feature when you're building a driver that it's worth using RegMap just to have access to that during the initial development of a driver. Where can we go from there? Okay, so we'll introduce function tracing. So function tracing is a step up. It is a bit more complicated for your customer to deploy, but it allows us to see further. So if we've not had much luck with the demessage trace, we can't figure out what to instrument, we want to go a bit deeper. What does function tracing do? So function tracing, the essence of the tool, I said I'd introduce you to the essence of the tools, is first off, you can compile all the code with -pg, which is the profiling hook. And that results in every single function call in what's called the preamble. So when you compile a function, there's a little bit of generated code the compiler will generate at the beginning of the function that sets us up to run the function, and then you will see the opcodes that map the operations you put in the actual C code. So it's things like stack allocation and perhaps argument management and register storage, things like that. But what happens when you have -pg is during that preamble, there will be a call to a special function called mcount, which is the profiling hook. If you have gprof, gprof library provides an implementation of mcount, and that's how gprof and pg work together. What happens in the kernel, however, is there's an interference, I think, in the linking stage. I've not actually looked at exactly which stage the interference happens, but the result is that by the time it ends up in the kernel binary, the branch link to the BL instruction has gone and has been replaced with a no-op. So when you load the kernel, you just get a no-op in place of that call. And the cost of that no-op, while it's disabled, is almost free. It is notoriously difficult to spot when ftrace is turned on because it's quite difficult to identify the performance loss associated with the no-op. It would be observed in things like iCache profiles. So if you have a workload that is on the ragged edge of whether it fits nicely in the iCache, that no-op will turn it over, could push it over the edge. It can also cause misalignment of functions, which means it could even go faster with no-op turned on if it just happens to be put a couple of critical functions at different alignments depending on your cache configuration. That's why it's hard to find. However, the kernel also has a data structure that tells it where all these no-ops are located. So as part of the k-all-sims thing, where it knows the name of each function and everything else, it also knows where the no-op is and how to change it to something else. So if you ask it to trace a function, the kernel will replace it with a branch linked to a function called ftracecaller. And ftracecaller allows the kernel to track every time we call a function. And that gives us some very powerful logging capabilities. So like I say, ftrace is fairly lightweight. It's just a few no-ops when it's inactive. But you can enable it using DebugFS. So once you've got it enabled, it will come up with just the no-ops, and with a couple of commands going into DebugFS, turning on the function tracer, and I think tracing on is there by default as well, actually. Just with a couple of simple shell commands, it can be set up, and you can start extracting data from it by cat trace, which is another file in this directory. I'm afraid I can't go into details on how to use ftrace. I have a full 2.5-hour talk on that as well. If it comes to it, it takes a long time to cover all that ftrace can do. But a couple of quick ideas for you. You can configure ftrace from the kernel command line, particularly useful if you want tracing to be active through the kernel initialization. So we can say something like ftrace equals function, which puts in the function tracer. And in this case, we've got a allow list. So ftrace_filter says, I only want to instrument functions that start with my drive. And this is assuming that we've got a driver that has a prefix on all the interesting functions, and it allows us to trace just those functions. That will not trace very much. This will give you very low trace volume, but it will let you know, for example, that a function has been called. One of the things you quite often want to know as a debug thing is, did my function get called? Has the error function been called? Has this function been called? Has it hit these paths? If you know functions are going to be called on particular code paths, you can go in and hunt that specific function. So this is very specific. We have the opposite. You can also do block list. So here we've got a no trace command. It happens to be a slightly different filter, but it's a no trace command. And we're telling it we don't want to instrument RCU, locks, and spin locks. And that's because when you're doing tracing, when you're doing lock debugging, calling lock APIs is really important, and it's very important to understand what's going on. When you are trying to understand code paths that the kernel has taken, they're just noise. There's so many of them. They're called all the time. They are the sort of thing that make it impossible to read the trace because there's just such a volume of it. So we can get rid of them. You can, of course, do both as well. You can have add the no-op, replace the no-ops in these functions, and then disable graphing in other spaces. But the exact way that these things interact, I'm not going to go into, except to reserve that I have also got ftrace equals function graph. This is a more powerful tracer. It hangs on exactly the same framework as this, except inside ftrace caller, it interferes with the return stack. And that causes us to re-enter the ftrace system when you exit as well. So in other words, the mechanism I've shown you here only instruments function entry. But once you have instrumented function entry, you can mess about with the return stack and instrument function return as well. And that then allows us to track every time we enter a function and every time we exit a function. It's a really, really powerful tracer. Once you have the trace can be extracted in a number of ways. It's accessible to user space, and there are things like shell scripts you can use, or trace command. Trace command is a front end that helps you configure ftrace without having to go through this file system directly or without having to use the kernel command line. It's another way that gives you a more command line oriented option flag based interface to configure function tracing. You can cause some trace to automatically route to print K, but you can't actually take the function trace. You can take trace points and put them to print K, but you can't take function calls into print K. So that's fairly minor. We can also arrange for the ftrace buffer to be dumped on certain critical occasions. So ftrace dump on oops is fantastic. If the kernel oopses, you can arrange for this massive trace to be dumped out via UART. It might take many, many minutes, but if you've got a UART logger set up, doesn't matter how long it takes, it will still give you some interesting information. And finally, if you're using KDB, KGDB is the kernel debugger that permits you to, via a serial port, attach another external GDB to it, and the debugger is running on the tethered machine and you're talking to the target. KDB is the on-target machine level debugger. So this is a debugger that runs on the target and allows you to interact with it at a machine level without having to have a second machine as anything other than a dumb terminal emulator. One of KDB's commands is to show you the ftrace buffer. So particularly if you are, say, a form factor device that you're going to carry around, a portable device, and when it fails, you want to take it, plug it in, and extract some data from it, then KDB does allow you to even do things like that. So instead of dump on oops, you can enter KDB on oops, and then when your system hangs, you can plug it in and try and find out what happened. Finally, when you've got this huge volume of trace, you need a way to navigate it. So trace print K is quite useful. That just allows you to inject a freeform string into the trace. If you've got that automated fail early device, it can say, I've passed, I've passed, I've passed, I've failed. And it can help you navigate the trace just by looking at particular things that have happened in the trace. Kernel Shark is really useful. Kernel Shark is a GUI that allows you to try and spot patterns within the trace by visualizing it. And then Lisa is a toolkit that is used by ARM for mostly for scheduler development and testing. But it includes a lot of modules that allow you to deeply analyze tracing. Lisa is a very high investment tool. It's basically a scientific computing mechanism, SkyPy, Jupyter, things like that, but able to process trace commands. So it's a way to bring together some of the notebook concepts from Jupyter alongside a trace database. So very powerful, very programmable, but a huge learning curve. Other things we could be doing to try and, in fact, the last thing that we could be doing to try and chase things down in this particular story is a crash dump, a post-mortem. So this is very much more for people with a server focus or a workstation who can afford to spare the memory. But KDump is a tool that is triggered using kexec. So kexec is a way for the kernel to load a different kernel into memory and jump into it. So it's roughly speaking using Linux as a bootloader to bootload a different Linux kernel. Kdump is a mechanism built on top of kexec that allows you to say, so when the system oopses or when the system panics, I would like you to automatically boot a completely different Linux kernel and then use that new Linux kernel to debug the memory image of the kernel that crashed. So the way it works is as the new kernel comes up, there's a special file called proc_vmcore, which is the memory image of the previous kernel. And that can just be loaded into crash tools and examined at will. So you can exfiltrate it however you like. You've got a file, proc_vmcore, and you could use network to copy it to another machine. You could store it to storage media. You could even automate, if you've got a storage driver, you could even automate the storage to it. The problem, of course, is that you do have to have the new kernel work sufficiently well. So this is a very common technique on big iron and mainframes as part of their serviceability approach. What happens on big iron tends to be you have a dedicated storage device to hold crashes. And then when it crashes, it will automatically copy vmcore onto the file system on the dedicated device and then reboot. So that they can chase the magic 99.9% uptime whilst also finding whatever kernel faults may or may not exist. The key thing here, however, is that the crash kernel has to have lots of RAM allocated to it. That's not just the RAM to store the tool itself, it's also the RAM that the kernel will use when it's booted to avoid corrupting the original kernel image. So it's a fantastically good tool for if the kernel panics, basically, it's a very, very effective way to be able to record what happened. But the cost is that it's sufficiently expensive in terms of memory that it's seldom used on embedded systems. Like I say, it's much more common on big iron. However, and sorry, just on the right-hand side, once you have a Kdump image, copy of vmcore, you can load it into things like GDB. You can load it into a thing called Crash, which is the tool that partners with Kdump. And Crash enriches GDB with things like thread awareness and capability to extract the ftrace buffer from the memory image and things like that. The reason this is also viable for embedded is that there are other tools you could use or build to gather the dump in the first place. Kdump produces a memory image. There are other things you could use to generate a memory image. For example, you could connect to a JTAG debugger and pull out the entire memory image over JTAG. You could have a magic bootloader that relies on kernel panic flushing the caches and then resetting, and the bootloader will then re-establish the DRAM refresh before its content fades. So it's quite possible to have bootloaders that program the refresh on the RAM sufficiently fast that the contents of RAM survive the reset. So providing you've dumped the cache, you can write bootloaders that effectively store dumps for you. Now, I can't go into detail or even give you references to any of these tools. They can be built. I know some vendors have built them, but they're something that typically the vendors have to invest in. And they're different. If it's different JTAG debugger, the technique to produce the core dump image from it will vary. So it's a significant investment that you're putting into this. So just stepping back, I've spotted another question come in. So there's a couple actually. So does the driver need to expose any special interface to support debugfs and register mapping from user space? The driver does not, but when you build the kernel, you obviously have to have debugfs turned on and the regmap feature that allows you to put the register map in. The driver does have to be using regmap. So regmap is an infrastructure to read and write from registers. It has a number of backends, including memory mapped registers, so it can be used for many, many drivers. But a driver does have to be using regmap to provide that feature. And the other one is to do with the interaction between modules and ftrace. So when a module is loaded, whatever filters you have in place, I think you would have to reconfigure the filters. So the kernel does not remember the wildcard. The kernel processes the wildcard at the point it is used. So where you have this wildcard here, it basically goes through KAuSIMS, it matches things to it, and then enables the trace to things that match. If you're doing a module load, then clearly the wildcard won't have matched anything in the module. So after the module load, I think you would have to cause some additional filtering to happen. Although, if you haven't put in a wildcard, bear in mind the always on one, in the case above here, the filter is actually a generic allow everything filter. So it would certainly work correctly with modules if you have the generic allow everything filter. But I think when you start using these filters, I don't think the patterns are what gets remembered. I think it's the specifics of what gets enabled or disabled. Okay, so just to finish up this, I'm going to stop for a break in a few minutes, but just to finish up this section, it is really, this is an aside really, but when we talk about things like kdump and crashing, we're talking about having some pointers. When we talk about oops traces, we're talking about having some pointers. Once you can see the physical values of pointers, it is very useful to know the memory map of a kernel. The memory map does actually change slightly depending on what page tables, what page sizes you have, and how many levels and how much address space you have got available to you. But if you are on a fairly standard normal 4-level 4K page kernel, then addresses start with 4 Fs. Everything in the kernel, that kernel addresses start with 4 Fs. Everything in user space starts with 4 zeros. If you have a mixture of values in those top of the address, what you're working with is not a pointer. So if you see the kernel dereference anything that doesn't start with Fs, you should be very, very suspicious unless you're actually in things like copy to user and copy from user. More than that, it's not just recognizing the Fs. The other thing that you can observe is the type of memory we're working with. So I talked about those big 2 meg pages. That's this thing at the bottom, the 7, the direct mapped kernel memory. So this is kernel memory that is directly mapped with big pages. It's how we access things like kmalloc would be allocated from this particular set of addresses. You'll notice, however, that the text and so on doesn't come from that space. It comes from the vmalloc space, which is what allows us to have kernel address space layout randomization. So from the vmalloc space, we expect to see some certain other things. There are particular bits of memory that have been created with particular properties. Anything that you use vmalloc for, you expect to come out. If you have virtual map stacks, what that means is the address of the stack will be F0 rather than F8. It's something you gain a little bit of experience of. Every time you see a pointer, it's worth thinking about where it came from. And I can give concrete examples. I was looking at a linked list a couple of months back and observed that one element of the list was atypical, meaning it had been allocated with a different allocator. So basically one of them, I can't remember which way around it was, but one of them was from the vmalloc space, the others were from the direct map kernel space. And that was sufficiently atypical, it looked like a mistake. Eventually we traced it back to a something that we added to the list from read-only data instead of being copied and added to the list, and that was actually a fault. And it was why why the list was becoming corrupted. So it is not, and it was more than that, this was actually also during this genuine story, the I can't reproduce but my customer can. I was helping somebody else, they'd sent me some stuff to read, and I just said, this is atypical, this is weird. We then used the source nav. This is still weird, it shouldn't be this type of pointer. And we eventually chased it down to this something in read-only data. So it doesn't happen every day, but being aware of what pointers look like can help you understand them. Similarly with stacks, it is useful to know how stacks work, especially if you are on a 32-bit ARM. So on a 64-bit ARM, it's not too bad. We have a 4K stack, and we have 2 stack registers, one for the kernel, and one that is normally used for user space, but on entry and exit to the kernel, we actually place it with a pointer to the task struct. Inside the task struct, we have the thread info, which is the fast place we use to find things about the current thread. The idea is that thread info is accessed much more frequently than the task structure, so we get to it quickly. ARM doesn't have the luxury of two different stack pointers that we can cheaply observe. So it's constructed differently. It has a stack. At the bottom of the stack is the thread info, and that's how we find out what thread we are. What that implies is if you overflow the stack, and it's accessed through this little bit manipulation. What that implies is if you overflow the stack on ARM, you can't even identify what task you are anymore because you start looking at a different thread info somewhere else in the system. So it's one of the things that makes stack info so exciting on ARM systems. It's why things like VMAP stack also work here, but don't work here as well. So just it's worth knowing that kind of thing, so that you're just aware to the possibility that when you do something like what task am I and you get crazy values back, it's one of the theories of what might have gone wrong. It's worth thinking about, basically. And with that, we get to our second story. Now, don't worry too much because the rest of the stories go a little bit faster than the ones we've looked at to date. So I'm going to take a very short break. It'll be 5 minutes basically. So I'll restart at hour. I will still be here in the room with you. If anybody has any questions, I'm quite happy to chat and talk about any questions that come in. But I'm not going to go back to the actual presented material until hour. Gives you a chance to stretch your legs, avoid the enormous deluge of information. We're aware this is a very fast-paced talk, and that's why we have slides. It's why we have lots of things for you to look in the background. Lots of springboards. But it does help to have a short break from something that's as information dense as what we have here. So I'm currently running to exactly the timescale that I ran when I delivered this morning, which is fine, but I did overrun by 10 minutes when I ran it this morning. And given I haven't managed to catch up during the first half of the presentation, I suspect we're gearing up to run over just by a little bit come the end. I will try not to, but there's no point in me speaking so fast nobody can keep track of what I'm saying. So I would rather overrun than just skip past things. So don't worry about it. I'd like to present the material, so I'll do my very best to get that through. Oh, fantastic! So somebody's pointed out in the chat that there is patches in place to do VMAP stacked for Arch ARM. Does that mean that there's page debug alloc coming as well? Because it was all kind of based on the fact that it was difficult to map the 30-bit systems have some difficult challenges when it comes to memory map, because there's a large amount of trade-off between how big this direct map kernel memory area is and how big the vmalloc is, because they're starved for address space. Then there's quite a lot of trade-off to be had about how much you map directly, how much you reserve for vmalloc, because quite often you can't map all of memory on a 32-bit system. So yes, great that they've got VMAP coming. I will read up and find out how they've done it. Obviously, I shan't read up dynamically while I'm presenting, but I would be interested to read that. In fact, I'm going to grab the link. There we go. Can I comment quickly on NG, NR, NE mappings? Oh, I could. So I can't remember what all these things stand for. That's a very army way to say device memory. So when you do an IO remap, essentially the virtual address space from which an IO remap comes is the same virtual address space that comes to vmalloc. The difference is in what tags are put on the page as it gets mapped. So that particular one, I believe, is it memory like? So the ultimately a couple of different ways you can map things. You can map them as device and uncached, which means that it looks like memory map peripherals. In other words, if you read from it spuriously, if you speculate reads, you do other kind of synthesized reads, harm can happen as you accidentally flush FIFOs. There is a second type of memory that is common in things like graphics cards. So the graphics cards video memory is mapped a different way again, because it is actually memory-like. It is safe to read. There's no FIFOs sitting in the space. You actually want to write combine when you write it to make the writes more efficient. So it's still uncached in some sense, but we are able to optimize certain of the reads and writes that we do to that memory. And then we've just got normal regular memory. I have to admit, I cannot remember what the G, the R, and the E specifically stand for. I think the N stands for not, but okay. So next story, my widget missed its deadline. So in this case, it's a slight, again, it's a deliberately vague story. It's important the widget gets handled quickly enough, and when the system gets busy, that is not happening, and we end up having something bad happen. You can see my set-top box heritage there because I said dropping frames, but there are lots of other bad things that can happen when we miss our deadlines. The Q&A team are beating me up because we promised this nice, smooth user interface. What we've left very vague. So we've left missed deadline as absolutely vague. We haven't said if it's an interrupt handler, a tasklet, real-time thread, regular task. We don't know, even scheduling activity on the GPU. We have not left it defined as to what deadline we have missed. Again, when the system gets busy is another very vague phrase. And vague phrase here, it could be system testing, could be synthetic workload. It could just be we're trying to power up the CPU and we're causing things to go wrong. We could be running Hackbench. The QA team beating me up does suggest this could well be a system test, which is the nature of being the QA team that are chasing us could be a system test, but it's not explicitly stated. We are going to make the assumption that the kernel remains functional throughout. In other words, we don't have to do any clever recovery of trace buffers. So we can trace as much as we like into RAM. We can use caches to store into RAM. We don't have to worry about post-reset memory recovery or anything like that. The kernel is going to survive enough to give us back our logs. And that's because it missed its deadline. It didn't say it crashed, it didn't say it went wrong, it's just missed its deadline. We're going to assume that in terms of failing early, that we can easily add code to the widget driver to say we've missed a deadline. When the widget, basically it's quite common. I'll use interrupts as an example. If you have an interrupt that is fired, audio interrupt, for example, it will know at the point it runs if it's underrun or not, if it's allowed the audio to fail. Because it can look at the passage of time and say, it's too long since I last ran. So basically at the point that whatever is being serviced does get scheduled or does get interrupted or does get serviced, we can look at the current wall time and say, oh, we've missed our deadline. So we're going to assume that we can fail early, we can record the point at which something bad happened. Logging a message at that point of failure time is going to be an enormous asset to help us navigate trace information. Now, apart from the message at point of failure, we're going to assume print K is not of much use here because it's going to be too hard for us to decide where to put the extra log messages. We can't just enrich the logs and look at the demessage trace now because we don't know where we need to put the trace. So we need to look for other ways of things could be going wrong. Now, obviously, you could just use ftrace. You could use ftrace or function graph tracing and find out what functions were running just before we missed the deadline. That would give us some clue of what the system was doing. It would be a very good technique. But we've already talked about that, so I'm not going to talk about that one again. I'm going to look at some of the other possibilities we can do with ftrace. So first off, we could go looking for trouble. If it is an interrupt handler that's running late, one of the obvious reasons for it not to work is because we are either running other interrupt handlers or because we've had interrupts turned off for long periods. So we could go looking for that. We could look for long periods where interrupts are turned off. We could look for periods where we don't preempt if it's a scheduling problem. We look for long periods of both. We can go looking for trouble, and if that's longer than our deadlines, we can try and fix it. You can actually also go looking for trouble in the scheduler by looking at long periods between a task being made runnable and the task executing. So for example, if we have a real-time thread that spends a long time waiting from being made runnable to actually getting onto the CPU, we can use wake-up-rt to try and find what's happening there and study it. Finally, we could look at static trace points. So static trace points are ways to convey additional information into the same ftrace buffers that the function tracer uses. So ftrace itself is a tracing subsystem. ftrace has a function tracer. It has a trace point logger. It has a bunch of other functionality. So we could look at static trace points, and static trace points I think you should regard as advice from kernel maintainers and developers about what is interesting in that particular code base. So for example, if you want to learn how I2C works, go and turn on the I2C trace points on your laptop and then touch your touchscreen, and you will see lots and lots of activity on the I2C bus as your I2C touchscreen does things. It's advice from experts. In the case, in particular, we have the scheduling trace points, which are basically all the interesting events that happen in the scheduler. Context switches, decision making, steering, lots and lots of bits like that. So if we turn on using this particular command here, the static trace points for the scheduler, we will have logs of things like context switches. We would be able to see who is going, what task we're running when we should have been running something else. Again, we get a better view of the system with much less overhead than doing a full function trace, because now we're only tracking a couple of particular points in the scheduler. I've seen a question come in about system tap. We don't mention system tap specifically, but we will bring in ePPF in some of the later questions, and that is used for some of these activities. Sorry, I've moved my mouse. There we go. Okay, so we've said that perf. Sorry, we haven't. We've said our widget. We've said that our widget has missed its deadline. Now, in the previous example with ftrace, we've assumed that the reason that it missed its deadline is because something is happening that we didn't want to be happening, and we've perhaps misprioritized, or just the system is doing something else when it should have been servicing our widget. If what we discover is what the widget was doing was servicing the previous, what was happening was when we should have been servicing the widget, we were still serving the widget from last time, i.e. we just can't run fast enough to keep up, we might turn to a profiler. So this is essentially, we can't run at real time because we haven't got enough performance to run at real time. At that point, we might build into perf. So perf is a profiling tool. Perf primarily exists to exploit performance counters, but it can also use things like timers, and timers are fundamental to time-based profiling. So timers are quite sufficient to do profiling. The essence of it tends to be built around periodic interrupts. They can either happen every n milliseconds or perhaps every n cache misses if you want to profile cache misses. But we're doing time-based profiles, so we assume it interrupts maybe 1,000 times a second, captures the program counter, and carries on. And by running that for a long period of time, we can find out which program counters and which functions are most likely to be executing. In the terminal on the right, so I was just seeing a question come in. On the terminal on the right, we're looking at a simple flat profile of the system where we're running something called perf top, which gives you a dynamic view of which are the hottest function on the system at the moment. In this case, it's brought out pulse audio because I believe this was running some kind of audio use case at the time, and because idle is not shown here. This would be a much less, that value would not show as high on the trace if we showed idle. This system was actually nearly idle, and all it's really doing is servicing pulse. I cannot possibly, again, go into all the details of how you can use perf to dig deeper into things. It's not just a flat profile, it can do function allocated profiles, so you can find out which call stacks are hottest and things like that. I've just offered some entry points that you could look up in things like man pages in the foil here. There's simply no way I can cover profiling in the depth necessary. But if something misses a deadline and it's because the performance isn't there, perf is one thing to look at. CPU freak would also come up as well. That would probably show up in the ftrace side. You might want to put in things like CPU freak and other performance changes as well as the scheduler. A very specialized type of profiler is just interesting to mention. I have to admit, I have never used the lockstat profiler to improve performance of my systems, but I know people who do. And it's basically trying to help identify heavily contended locks and data sharing, so that you can redesign some of your algorithms to be better behaved. And so you would only bring this out, of course, if you're seeing locking as a significant contributor to your profile, and you're trying to get rid of lock-based costs. So you found something in perf that says, oh, those locks are looking a bit expensive. Then we can start profiling to try and find out which ones are the contended lock, why, and so on and so forth. So this is a very, very specialized tool, but while we were talking about profilers, I wanted to bring it out. There's a comment about K and J probes on functions. I don't actually understand the question, I'm afraid, there, so I don't know what it was reacting to. If something else comes in, I'll comment on it. So we've been looking at using traces to try and find out what the system was doing when we've missed our deadline. We've looked at ftrace, we've looked at a couple of other things. We can bring in CoreSight as well. So CoreSight is hardware-based trace. CoreSight is ARM's family of debug technologies. But one of the things that happens is almost all Cortex cores have a thing called the embedded trace macro cell attached to them. And it basically gathers jump trace information. Every time the Cortex core adopts a new basic block, so every time it jumps, it stores an event in the trace system and propagates it to this hardware funnel, where it gathers together all the trace information from the different cores together with software generated trace. So if you want to have navigational information like context switching, so when you're on a virtual memory operating system and you want to understand jump tracing, you have to tell it when we have changed context, because that means we're changing address space if we want to trace user space as well. So every time we change address space, we get software events coming in to help us interpret the information in the trace capture buffer. And the trace capture buffer can go to multiple places. It can go to expensive pieces of specialized hardware, Lecterback being the name that usually comes up at that point. It can also go to memory. It can be recorded out and pumped into the system's own memory. So that's where these things come up most often. So again, I can't go into detail of this. There are hour-long presentations from various Linaro staff at a couple of different connects. But ultimately, the OpenCSD library is there to help parse the information that comes out of these ETMs. And it is fully integrated into the trace tool. So if you have a kernel in which CoreSight has been properly enabled, and you have an appropriate piece of hardware on the outside here to store to memory, CoreSight is quite interesting because vendors have a lot of control of how it's been implemented. So the ETM is part of the hard macro cells for the Cortex core. So if you're not an architecture licensee, you almost always have an ETM. But how your Cortex system is, so CoreSight system is integrated after the funnel can vary. It's up to the vendor how they implement it. So they may or may not have means to exfiltrate it via the various different mechanisms. But anyway, if you have a well-designed CoreSight system that can trace to memory and the drivers are present to enable it, then by turning on perf, you can do very strong trace. This is more powerful even than ftrace, but it's generation hardware, it's cheaper to gather, it has slightly less intrusion ultimately. And then finally, eBPF. And you can read, there's a question about system tap. You can read system tap as being in a similar place. System tap can actually generate eBPF opcodes if necessary. So it's a different technological underpinning, but it actually addresses similar use cases. I don't tend to use system tap on embedded systems because it's very rarely integrated well enough that you can make it work. So it's not there's anything wrong with system tap. System tap is excellent. But my experience on embedded systems was the pain of getting to work wasn't matched to the benefit I got from it. So just an idea of the world without eBPF. So without eBPF, what we're doing, if we're doing any kind of profiling or analysis of the system, is we're gathering a whole bunch of events. We're using ftrace events as an example. They're going to buffers. They're being thrown into user space. The user space is perhaps stored into the disk or to RAM somewhere. And eventually it goes into event processing to synthesize some statistics for us to help us understand why we've missed our deadline. We could write a single program, inject it into the kernel, and have the kernel gather these informations. So eBPF is simply a virtual machine that sits in the kernel with a strong verifier to make it very, very difficult to break the kernel as a result of loading an eBPF program. To the extent they even control the number of opcodes that you can execute so that you're guaranteed to have a bounded execution time. So even locking the kernel with denial of service is not impossible, but difficult with eBPF. It's very hard to accidentally make mistakes. And this is where we get a strong split between the between people who routinely expect to recompile the kernel, which means most embedded developers, and people who expect to get the kernel for them, which means most server-oriented and data center developers. If recompiling the kernel is not the norm, then BPF is absolutely fantastic because it's a really powerful technology that allows you to inject actions on things like kprobes, gather some information, and then continue on and extract information. There's a book by a chap called Brendan Gregg that introduces all this. It's called BPF Performance Tools. That use case really makes sense if you are not used to recompiling the kernel. The main and truthful answer of why I don't use system tap very often is because it competes with just writing in C and recompiling the kernel. And as a person with a strong embedded history, if it's difficult to set up the tool and it's competing with just recompiling the kernel with some instrumentation, I will almost always recompile the kernel instrumentation. BPF has reached the level where with tools like BPF Trace and some of the libbpf based tooling, they are comfortable and easy to deliver onto specific platforms. And that does make a big difference to their deployability. But for the embedded person, the capacity to add code to the kernel is normal. You routinely recompile the kernel several times a day. So having a virtual machine does still offer some benefits to the embedded developer. The fact it's so hard to crash the kernel means that you perhaps spend less time debugging your own debugging code, because if your debugging code crashes, you've got to figure out why, how, and then debug the debugging code before you can use it to debug things. Because it's so hard to crash with eBPF, although the output might be junk, you're very unlikely to take down the kernel when you use it. The other thing that eBPF brings, which does apply to the embedded community as well, is the capacity to use it to make tools with it. Rather than it just being a thing that you have to learn how to use, you have to learn the special languages, you learn BPF trace, you learn how to write dtrace-like hooks that examine the system. No, you can take part in a community of tool developers that allow you to develop and run analysis tools quite quickly, and you can share them with others. So in particular, look at the BCC family of tools, where some of them are being rewritten. So the cutting edge of eBPF at the moment is something called code once, run everywhere, CO-RE, and it's based on decoupling BPF from the specific version of the kernel you're going to run the tool on. And that itself is based on specific types of debug information that have slowly been embedded into the kernel. Those tools, these core tools that are being put together for the BCC collection of tools, means that you can go and find tools to do certain types of analysis. And if that's the analysis you want to do, in this case, we've got a power analysis that is showing the residency in each power state, which is not impossible to write within the mechanisms, but it's an example. So BPF is not simply a tool for you to use, it's also a tool for tool makers to use. And then you can learn their knowledge by reading the tools that they've built and deploying the tools that they've built. Okay, so we move on to another story My board just stopped dead. This is a one that will be familiar to a great many embedded developers. So it's running fine, and it stopped. No kernel messages, no console messages. I can't even figure out how to make it talk to me enough to extract the old message buffer. So it's not reacting to my input. I can't stimulate it to do anything. It's just stopped. It's gone quiet on us. I hope I've addressed the system tap question. It sits, like I say, it sits in a family of tools similar to things like BPF trace. So a lot of what I've said about BPF might apply to it on a server platform, but the specific answer is usual for me to use system tap, and as an embedded developer, no, because it was too complicated to deploy and it was competing against building the kernel yourself. So my board just stopped dead. So this is deliberately a very wide thing. We don't know why the machine has stopped talking to us. We will assume that the hardware is not faulty. That doesn't mean it's not a hardware failure. It could be a bus lockup. We could have tried in software to touch a particular address and the bus has failed, but that would be deterministic. Every time we touch that point on the bus, we expect the bus to fail. What we're not expecting to see here is things like memory that doesn't give us the same value every time we read it, or buses that potentially lose top or bottom bits as they transit data through them. So we're assuming the hardware is reliable. We will come back to that for the final pieces. The details of this story then are very device specific as well. There are lots of reasons for boards to stop. There will inevitably be information about the system that we need to know to reason about what might be happening. The board state is not known. So what I mean by that is we don't know that the buses are still running. We don't know about bus health. We don't know what power state it's in. One reason for boards to stop dead is when they turn off their own regulators. That is quite whimsical. So we don't know why the board isn't running. We don't know what state it's in. And it's also useful to, this is where we introduce the concept of, I like to show you the essence of tools and how they work. Because when they don't work, you can use the fact they're not working to reason about how badly the system has crashed. We'll come to what that means in a minute. So initial analysis, firstly, fail early. So fail early does make a lot of sense in this case. If we could try and figure out what happened while we still have printf working, that would be great. But we can also have a theory. The theory is that printk itself is still working, but nobody is calling it. And that's a reasonable hypothesis. It's not guaranteed to be true, but usually when the board stops dead, it's because it has stopped executing code. And if it stops executing code, it will never call printk. So the trick is, how can we arrange for it to call printk at certain critical points so we're likely to get some clues about what's going on? Now, first off, we should bring in if the problem is occurring during boot. So if the system is not able to boot completely, it's stopping partway through a boot as you're trying to bring up a board, then first off, early con is a must. Early con is a mechanism to get the serial port running earlier in the boot than it would otherwise. And init call debug is another fantastically good tool for trying to find out what's going on during the boot. Init call debug simply means that whenever a driver is called during init, the fact that we've gone in to call that init call, which is usually driver registration and a bus setup, the fact that we've run this init call gets logged to printk. So that can hone us in very, very quickly on which driver which is being probed is causing us trouble. The other thing that we need to think about if it's failing during boot is the clock subsystem. It's quite a famous behavior of the clock subsystem, and I think more recently the regulator subsystem as well, that the bootloader comes up, it establishes the critical clocks in the system. We establish the critical clocks and the system boots successfully. And then at the end of the boot process, the clock subsystem looks to see which clocks are marked as being in use, and it turns off all the other clocks to save power. If we have mismanaged the clocks, if the drivers the drivers that activate some of the critical clocks are not present, or we didn't correctly tag the critical clocks in the device tree, then we hit this clock disable unused function, the system stops dead because we stop clocking memory or something like that. So if you have that kind of behavior, we get through most of it and then it just stops while it is trying to finalize the boot after all the init calls have run. You always experimentally run with clock ignore unused, and like I say, these days I would want to go and reread how the regulator subsystem works, but I'm not able to speak on it authoritatively at the moment. And you add these command line options, and then clock disable unused stops disabling unused clocks, and you can try and find out what clock is being removed and get it correctly marked up as a system critical clock. You should always turn on a couple of fail early techniques. I don't know why I put debug mutex here. I think I'm going to say debug atomic sleep as being the most critical things to be looking at. Sorry, that's just a change of heart. Debug mutex doesn't cover nearly as much useful things as they should. So debug atomic sleep lockup detector, a couple of things from fail early. Have a look through the kernel hacking directory. Look for other things you could turn on if they will fit on your machine. You could even consider reintroducing debug spin lock. So debug spin lock is a debug technique that was removed from the kernel, and it was basically just a timeout on spin locks. So if it spent more than five seconds trying to lock a spin lock, it would print to the screen. That's a really useful way to find out if something's got stuck waiting for a spin lock. The reason it was removed is for big iron machines. When you've got big iron, if you have a highly contended spin lock, what's the longest you can wait? It can be many seconds. If you've got hundreds of CPUs hammering away at spin locks, there's high contention. A, you should probably try and get rid of the contention, but B, you can't know how long it takes. So this was notorious for false positives, so it got removed because it used to cause this trouble of false positives. It also made spin lock thrashing worse because it means you have to use slightly less efficient spin lock entry protocols. However, on small embedded machines, on small numbers of cores, it is something you could consider reintroducing to get you that print K, but that you want. The other tricksy technique that comes up occasionally is to add a rate limited printf to the interrupt controller driver. Basically just to print the interrupt number that we're about to service. And that will bring up situations where you lock up handling an interrupt. So one reason that you can stop dead is you've hit an error handling the interrupt. You've hit an error path in the interrupt handler. You've then exited the interrupt handler, telling the kernel that you've serviced the interrupt when you didn't actually service it. And that will result in you immediately re-entering the interrupt handler. And like I say, that I like this rate limited print. It means every 5 seconds you get this little burst of I'm handling some interrupts, and then it goes quiet for 5 seconds. And providing those little bursts of prints aren't enough to damage the system, then we can find out what happened. We can see that we're stuck servicing interrupt number 178 or whatever it is. So that's some of the fairly early ideas. The other elephant in the room is the JTAG debugger. So if you have a JTAG debugger and your board has just stopped dead, connect the JTAG debugger and try and extract a backtrace. For people who have a JTAG debugger, this will seem incredibly obvious. But the nature of Linux programmers is it is very common for us to work on boards where we're a bit fuzzy about how to attach the JTAG debugger, because so many of the debug tools are self-hosted. Even where there is a JTAG socket, we might not know how to use it. We might have to go and find somebody else. Quite often, there's only a couple of JTAG debuggers and they sit in a cupboard in a lab somewhere, and only 4 developers actually know how to use them. If you're looking at investing a couple of, this can take quite a long time to think. If you've done some basic triage and you don't see it, you don't know what has happened. You've done some basic triage and you're stuck. It's worth investing the time trying to figure out how to run a JTAG debugger. Talk to colleagues, find out if anybody knows the config scripts, etc., etc. So again, I'm not going to talk a lot about JTAG debuggers in this course for the same reason we're not going to talk very much about KGDB, is that I think stop the world debuggers are what everybody thinks of when you talk about debuggers, and this particular training is about enlarging the view and bringing so many other tools to bear on trying to solve problems. So a JTAG debugger is a stop the world debugger that is implemented using a piece of hardware that makes it very reliable. If you have one, it's the best way to get a backtrace and find out what you are stuck doing. If you don't have a JTAG debugger, we can start using other parts of the system to reason about what might be happening. So with the exception of the JTAG debugger, almost all Linux debug tools are software based. Even with the JTAG debugger, it has to access memory. Most of that has to access the L1 and L2 caches to discover information about the system. If there is a bus hang in the place, then although you might be able to extract a little bit of information from the JTAG debugger, as soon as you try to do something like get a backtrace, its own bus initiator will also lock up and you'll be stuck anyway. So if you have bus hangs, that kills software. So kernel engineers do need to understand how to use kind of SOC level debug techniques to try and manage if you have bus hangs. So by a bus hang, what I mean is basically you've made an access to memory that doesn't exist, and because of a bug in the bus infrastructure, it doesn't report that as an error, it just ignores you, and then the CPU sits there waiting forever for the bus to commit and to grant it access, and it never happens. That's the essence of a bus hang. Modern buses are tremendously complicated. They're actually essentially packet switch trees, much like networks. And you can have bus lockups that only affect a subtree. Because they are these fairly complicated tree-like networks, you can have fragments break without the whole thing breaking, which is why we get into looking at other non-CPU bus initiators. So firstly, they can be used to provide clues about what's still functioning. For example, if you have an LCD that refreshes directly from DDR using DMA, and it still has an image on it, that means your DDR might still be working. This does require you to understand the hardware topology of the system. It won't always be the case, but there are certainly plenty of systems where the LCD refreshes from a frame buffer continually, and if the bus crashes, the LCD panel stops displaying things. So if that's the sort of hardware you have, then if you can see an image on the LCD, that means the DDR has not crashed. The DDR controller is still working. That can be a useful bit of information. More usefully, if a SOC has built-in co-processors, then they are likely to be able to make memory mapped access to the system. If they have a serial port or other ways to communicate outside of the Linux domain, you can even use them to implement peaks and pokes, which can allow you to look for which bits of the bus are still functioning and so on and so forth. It's off topic, but Linux can also return the favor. If you have co-processors in your system, make absolutely sure that there is a driver that can gather a core dump from the coprocessor, so that if the coprocessor crashes, you can exfiltrate that back and give it to the firmware team to get the coprocessor fixed. Other things you can do SOC level debug, things like post reset memory recovery. We've given some hints about this already. The bootloader, if it can reboot fast enough, can keep the refreshes running on the sorry, I'm moving ahead. Post-reset memory recovery. First and simply, if you have SRAM on the chip, if there's any little on-chip SRAMs, quite often they're for trust zone, but if you've not got trust zone enabled, you can use them for debug as well. If you have any on-chip SRAM, you can potentially hack trace tools to try and target SRAM. This does mean reaching in and just violently changing the kernel and how it allocates trace buffers. But if you're tracing into on-chip SRAM, SRAM is nice and fast. It's similar performance to a cache usually, which makes it comfortable to read and write to. Likewise, if you're not in the SRAM, you can potentially get the contents of DDR to survive during a reset. The big problem with that is that caches are going to be in your way. Caches frustrate post-reset memory recovery, because while a reset can preserve the contents of RAM, a reset will always destroy whatever's in the cache. So that means that if you're relying on post-reset memory recovery, you end up having to add additional cache flushes to things like tracing logic. And finally, this is another thing that I could mention may exist, but I couldn't give you details. For most SOCs, I don't know the details. And even for SOCs where I might know the details, I'd be under some kind of NDA that wouldn't allow me to tell you anyway. So I have to talk in abstract terms. But buses are these complicated tree structures. They need to be performance tuned. They need to be monitored. The SOC vendor needs to figure out how to balance the bandwidth between all the different components in the system. They quite often have registers that help the vendor understand the bus health, particularly so they can tune the bandwidth running through the bus in different ways. They are quite often secret because the vendors have put a lot of effort into trying to tune the buses, and they are aware that some customers will try to over-tune buses and then create rather obscure bugs that makes their support very expensive. So, like I say, if you work for a vendor, ask your colleagues about it. If you are using a product that comes from a vendor, you might be able to ask them if you present with bus hangs, it's worth contacting their technical support department to find out what they can tell you about. They may not be able to tell you anything. They may not exist. It's not that you shouldn't trust them if they say you can't do it, but there may well be registers in the system that allow you to understand which parts of the bus are still running. Okay, so other things we could do. So ftrace would be really nice. It would just tell us what the last function we jumped into was, which would help us reason out what was executing at the point we failed. The problem is that we've stored it in cache memory, and after a reset, it will break things. So RAM often survives a reset, but the caches will be destroyed. We've talked about that already. If we can find a way to access the ftrace buffer from other bus initiators that are cache coherent, that would be great. So there are quite a lot of cache coherent peripherals on modern systems. If we've got a JTAG debugger, that might be able to access memory in a cache coherent way, although many of them do use the same bus initiator as the CPU, which means if the CPU is stuck, so is a JTAG debugger. Could reach into a different cluster though. If you've got multiple clusters, you might get a chance. But overall, we need to find a way to store the trace where we can find it. One option is RAMOOPS. So RAMOOPS is a general framework for having persistent RAM, which will then be accessed, I think, uncached on the target, so that when we store things into the RAMOOPS buffer, A, we don't have to worry about flushing the cache, and B, it will, hopefully it will survive post reset. And we can even have, because it's a well-known, well-located piece of RAM, we can actually preserve it during reset and present it back to the user by just mounting it as a file system after we've rebooted. So it's quite a neat bit of technology. It's got some options that you can point it and address, you can tell it the size, etc., etc. All that means is that the kernel will map it non-cached, and we're relying on the bootloader to keep that address still functional after reset. It must be mentioned that full function tracing into that little ftrace buffer that we've got in our RAMOOPS buffer can be catastrophically performance damaging. So we have an example where we try to do a really aggressive ftrace. So rather than doing a targeted careful ftrace or just maybe tracing context switches, I think we pointed a full function graph trace and tried to store that in the buffer just to see how bad it could get. And we were seeing a couple of orders of magnitude in performance degradation. Hackbench was showing completion times going up from slightly less than a second to over 120 seconds. So big differences in performance are possible as a result of tracing to uncached memory. But if you're cautious about what you ftrace, this is still a very viable technique to try and figure out what was happening at the point we failed. Sorry, I thought there was an extra slide there, but it's not, so I'll have to just talk about it. So we talked about the scheduler trace points. Scheduler trace points are a very good thing to put in the ftrace buffer because they're not as frequent as something like a function graph. That can tell us the thread that was running when it broke. Once we know the thread that's running, we can try and figure out what code it was likely to be executing. We can do a much more narrow ftrace. We can actually, if it's a long running thread, we can even get ftrace to target specific PIDs. So it will only trace the thread we know is going to break. So yeah, there are things we can do to make the RAMOOPS more likely to be caught. So a quick aside into how to read an OOPS. Given we're saying we're going to store this RAMOOPS, it's worth just briefly going on to an aside about how we store the RAMOOPS. So we've put in bold some of the things that we think are most worth reading. Obviously, the reason we have OOPS is fundamental. Quite often, these use very hardware-centric phraseology. This one's not too bad, actually, the kernel null pointer. But yes, it might just say data abort or imprecise abort. Or if you don't understand the exact phrase that's coming up or what to use this number for, it's worth having a look at the architecture manual and finding out what these things mean. In this case, this is the exception syndrome register. So you can look up exactly what that means. It's actually composed a lot of it already to tell you what they expand to. And all these magic acronyms here, you can go and look up in the architecture manual if you need to know them. If the top is very, very clear, we've just hit a null pointer. We don't need to know what all this is, but you can dig deeper if the top bit is not readily understandable. The other thing I pick out is the 4K pages, 48-bit virtual addresses. We need to know our memory map. That is what tells us what the memory map is ultimately, because with different page sizes and different virtual address space sizes, we can end up with different characteristics in the function pointers, particularly if you go up to something like 56-bit virtual addresses, or 52-bit virtual addresses, sorry. So that's the first part. There is going to be a not tainted coming up at some point. Not tainted is not very interesting, but if it is tainted, it does become interesting. So a lot of people think of taints as the thing that tells you if you've loaded a non-GPL module, but there is more to it than that. There are flags that are sticky when certain of the debug things have triggered. So for example, if the lockup detector has detected a soft lockup, there's a taint called taint called L. If we have force loaded a module, which doesn't just mean a GPL force, but simply loading something against the advice of the module system, again, it will taint the kernel. So if you're worried that there's something before the logs that we've managed to capture that that might be the cause of the problem, the taint will tell us that something bad has happened in the past. Then we get down into things like the register dump and all the offsets into assembler. So here we are in the sysrec handle crash function at 20 hex, so 32 bytes past the start of the function. So we can do a couple of things. We can use things like GDB on VM Linux, just to use it as a symbol handling tool. So we don't have to use GDB as a full debugger. We can just fire it up and use it to study the symbol database. So this particular command line will fire up the debugger, but it will not connect to a target. But it allows us to do things like list addresses. So we can get the source listings that corresponds to a particular address. We can disassemble it with source code intermixed. So this disassemble /s will show us the opcodes of sysrec handle crash intermixed with the C code that it thinks attaches to each line. We can also use things like addr to line to try and convert addresses to symbols. That's there. So I've got me ordering wrong. I will come back to that. The other thing that we can do with these registers is try to extract function arguments. And now sysrec handle crash is not the best example of this because it doesn't have very many interesting arguments. But ultimately, on a 64-bit ARM system, the first 8 parameters, if they are not structures, are going to be stored in the first 8 registers. So the first argument to function gets stored in X0. You do need to be able to read a little tiny piece of assembler to find out if X0 has been modified. But that's actually not too bad if we've got a preamble somewhere. We've got a preamble. There we go. You know, you can see that that doesn't use X0. You can see that by the time we get down to here, X0 gets used for the first time. So, or W0 gets used for the first time. You don't need to know very much assembler to observe that registers are being used. And if they're not being used, that means that the registers still contain the arguments that were there when the function was called. So that can be very useful. The capacity to convert without having to use a tool from the function to its own arguments, particularly when you have functions that take context pointers. You can observe that the context pointer is invalid, for example. That's a really strong clue that you've read something wrong or something like that. So X7 to X0, very much pay attention to them. We have got them summarized here. So if you're an ARM 32-bit system, the parameter results registers, there's only 4 of them. They're the ones to really care about. These are useful to some people who are very skilled at reading assembler. You can use some of the other properties here to reason about things. But for people who are not expert ARM disassemblers, can't eyeball the disassembly and understand what it's doing, it is still possible to get to C-level parameters, and that's really, really useful. The other one that's valuable is the link register. So if the program counter is bad, the link register is good, that's usually a following of a bad function pointer. So if you followed a bad function pointer, the link register contains the place we followed it from. because when you call a function pointer, that's a function entry. So we have to record on the stack where we've been, and that gets stored in the link register. So where you have a bad program counter, the link register is going to give you the place where you called from. That's the other big thing we get from oops is if we've gone to a null pointer program counter, that's almost certainly a bad function pointer, and we can find out what function pointer we're following by looking at the link register. Exactly the same principles for ARM64. Again, there are a wider variety of components involved. The ARM64 procedural call standard does have a frame pointer that is almost always enabled. There are frame pointers in 32-bit ARM, but most people disable them, whereas frame pointer is almost always engaged on ARM systems, which does give us things like fast back traces. It helps profiles run efficiently and so on, but we don't often need to follow them manually because most of the tools will do that for us. But we do have, again, these parameter registers that allow us to try and figure out what's happening to our C parameters. We have the link register. They all act the same as they do on ARM32. So a quick scan of this one tells us the program count is good. That's excellent. We can look at the stack and see that's where I expect a stack to be on a not VMAP system. This one wasn't a VMAP system. X8 is not a pointer. That's okay. X8 is used for structure return. So it's when you return a structure by value, what actually happens is you allocate the structure on the stack and you put a pointer to it in X8. It's quite a convoluted dance. But then you've got the arguments that these things could be arguments. It could be this key value. Now, this is a terrible example, but it's one that's easy to make it crash. The reason it's not a great example on how to decode the arguments is because the key is unused, which means that the compiler has no particular motivation to preserve it. Because it's unused, the compiler is likely to overwrite it. So I'll come back to that aside in a second. So what we can see here, we can actually follow this down, and you can see at +16, it overwrites the content of W0. On ARM systems, W0 is a synonym for X0 that only accesses the bottom 32 bits. It's the only thing you really have to know to be able to scan the assembler to figure out if a register has been modified. In this case, we can see that at +16, the register has been modified, which means ultimately that is not the argument that came to the function. So we were able to rule out on this occasion that that's the argument that came in the cub function. Instead, we can see that it's just stored the force panic value ready to write to whoever it's going to write it to. Sorry for the jumping back and forth through the slides. I keep being, I'm just ready to tell you about this, and then I realize it's on the wrong slide. When you are decoding these sysrec handle crash plus offset things, you can use the tools I showed you before, GDB and addr to line. There is actually a script. Scripts decode stack trace. You hand it the oops and the VM Linux file. And if it's got debug information in the VM Linux file, as in you've got config debug info set, it will be able to convert those from hex offsets to function, file name, and line. So if you want to get that bridge between the oops and the C, that's going to be the best the debugger can do for you. Now, bear in mind that the kernel is compiled optimization turned on, which means the line number should be regarded as advisory. It's the best the debugger can do. The line number may not be entirely exact. You then have to keep your wits about you, and debugging optimized code is a bit of an art, but it will give you a much better view of the C than not knowing. So yeah, it can jump you into a line and get you a much better sense of what's going on, but don't assume that the line number is correct. Check. You can look in the arguments. You can say, okay, so that should be doing something. You could then say it's a pointer dereference. It's this. Does it make sense? Does the values make sense? Is it taking a kernel address and adding a number to it? That kind of thing. It's why we need to be able to recognize addresses and other things. Okay, and the final thing that comes up is converting binary code to instructions. So at the bottom of a stack trace, there is also this little code fragment, which is basically the opcodes that it was executing at the point something went wrong. There isn't a disassembler built into the kernel, so we're going to have to disassemble this ourselves, but we can use the tools to do it. We can effectively convert those words. We could use a script to absorb them and produce a fragment of assembler. we could assemble the fragment, and then we could disassemble the fragment, and we would see the opcodes that it was running. In this case, you can see the strut BW0X1, which is the same strut BW0X1 that we got when we disassembled the same code to find out what was going on in this particular example here. Sorry, I've lost place. There we are. Yeah, so that's a lengthy aside about oops traces. I hope it was useful. We're now coming to the kind of final straight of bits of stuff we want to mention in the stories. So CoreSight still has a few tricks we can put up our sleeves. Firstly, when the board stops dead, if you are tracing to an off-chip capture device, then the off-chip capture device will have recorded the last jump trace. So if you have a letter back in the cupboard or some equivalent piece of technology that allows you to capture the vast traces that come off the hardware trace systems, talk to people and figure out if you can plug it in. It is another very quick way to get to the full answer with tools. The problem is that, like I say, very few people have a letter back in the cupboard, and even fewer people who can find the cupboard know how to use it. You have to work with the tools provider to find the docs for that. However, CoreSight does have one final trick up its sleeve, and that is the debug registers that Stop the World debuggers use to interact with the target are memory mapped. Having memory mapped debug registers means that we can read things like the final program counter that was used on the target knew about, the final jump the target made, which has been very, very, very close to the point of failure. And more than that, so it's memory mapped. That means that if you have any bus initiator at all that you can control, even a simple peek and poke from a microcontroller, you can go and find the CoreSight debug registers with your microcontroller, and you can read out the program counter that execution unit was running just before it failed. The program counter, particularly if it's running in the kernel, can be really, really useful. Even if it's running in user space, you have got the problem of the fact that it's a virtual address space, but you can still narrow things down a bit if you know what target's running in user space as well. More than that, there is actually a kernel config option, CoreSight CPU debug, which allows SMP partners to watch each other. So if you have a soft lockup or you have a RCU update stall, CoreSight CPU debug can observe that the other processor is suffering and tell you what the other processor's previous opcode was. It's a way to bring out just that little bit of information onto the print K buffer after it stopped dead. So if you have any kind of lockup information coming out, so it's not fully dead, it's now giving you lockup information to say, I've locked up, but I don't know how. Then adding this CoreSight CPU debug might just get you that final detail of what the broken core was executing just before it stopped. Okay, so I'm sure this used to work. This is a nice narrow story. It is somebody who ran a test a couple of weeks ago. It ran perfectly, and they are now running it again, and it has broken. They're sure it used to work. This is a fairly narrow scope because we can use empirical methods. We don't have to actually understand the bug. We can empirically try to study the behavior of before and after until we understand what change it was that provoked the bug. So, like I say, it's relatively narrow because we know how to produce it. We know how to produce the failure, and hopefully we've got some idea of how to make it work. The reporter has been doing ad hoc testing quite clearly, so they may not have been entirely rigorous about configuration management. What I mean by that is the kernel source is usually fairly strongly controlled. We kind of expect to have Git, and we've usually got people who've got quite good working practices in Git. Things they might not have controlled quite so carefully are the kernel configuration. It's quite common to turn on a couple of extra pieces in your kconfig and then not find out that there were associated regressions until a couple of weeks later. Again, compiler updates, toolset updates. And in the case of kernel developers, they can be surprisingly blind to the existence of user space, i.e. you may have just upgraded your user space and it's now tickling a kernel bug that it wasn't tickling before, and you forgot that 2 weeks ago you updated your user space. Kernel developers can be very blind to the fact that the user space exists. So tools we can bring to bear on this. Git bisect will always come up as a tool. This is a tool to say this kernel is broken, this kernel works. Try and find which commit it is that has caused it to break. It's a fundamental and powerful tool. Couple of remarks from me about it are the fact that I never personally run git bisect good and git bisect bad, because I am too error prone. If I am doing a large complicated kernel bisect, I am not able to be 100% sure at the end of the process that I got all the goods and all the bads correct. And if you don't get all the goods and all the bads correct, then the bisect will lead you to the wrong commit, and then it will tell you it has failed. And if you spend a day and a half running boot, test, good, bad, boot, test, good, bad, boot, test, good, bad, it's really, really soul destroying to realize you've got to do it again. So the way I would suggest everybody operates is by writing a shell script to compile the kernel and run the test. So this will build the kernel and then launch a test. I'm aware that not everybody has relays and button pushers and other things attached to their test hardware, their device under test. So there may be manual steps involved in this. It may be a power supply cycle, it may be pressing a button, it may be the nerve pinch you have to do on some of the 96 boards to put them into download mode. It can have manual test. Get the shell script to tell you to do the manual test. So to do the manual step, perform the manual step, and then let it figure out what the verdict is. That is both much more, what's the word? It's much less error prone, and it means instead of you spending the day watching carefully what's going on, you pick out an interesting textbook. This is the BPF one that I mentioned earlier, and you sit and you do some personal development with your textbook, and you make sure your screen never goes to screensaver, and so that every time it asks you to do the manual step, you can do the manual step, and then you can carry on. It's good for your attention, it's good for accuracy. It's just important not to be doing something on the same computer, because then you will switch virtual workspaces and you won't see that it's waiting for your attention. But basically try and find a way to be there when the computer needs you to run the manual step, but that you're doing something useful in the gaps. That's just a much better way to work. One thing that's been added relatively recently to Git bisect is something called stochastic bisect, which is where you have test cases that are imperfect. They only fail 80% of the time, which means you can't say something is good or bad, but you can say it's 80% likely to be bad or good. I've not got anything in the slides about stochastic bisect. There is a fantastically good LWN article on it. But if you are working with test cases that are not absolutely reliable, I would very much encourage you to go and read up on stochastic bisect, because you can build these same shell scripts to run them, and you just say run them until you're 99% confident that you've got the right bisection, and then it will crunch the stats and do its best to give you that answer. Okay, so moving on to other things that could happen. So I've mentioned that our developer in this case may not have been entirely disciplined. It is possible they will eventually finally figure out that there is nothing in the kernel that's causing the problem to go away. It is actually a change to the config files that they've been working with. Hopefully they can find a before and an after. And at that point, they now potentially have quite a big difference. Sometimes config files have had some very big changes in them between the working and the broken cases. So ktest.perl is a very interesting thing to bring in at this point. It's a framework for running automatic tests on target boards. Some of them are really quite cool. But one of the things built into it is a capacity to bisect config files to try and establish which config value it is that causes a problem to appear or disappear. It's an idiosyncratic framework, so it does assume that there's certain levels of automation that you have available to you. It can be hard to get to work. It's also got no documentation. But it does have samples config with lots and lots of comments and examples in how to use it. So if you have got a complex config bisection to do, it is well worth a look. And we're heading through the final slightly anticlimactic finish in the last story, which is my board just randomly failed. So this is where we reintroduce the idea that perhaps the DDR configuration isn't perfect and it will sometimes give us the wrong answer. It's where we bring in probabilistic failures that are not software related. So the board is randomly failing. We're not doing anything special, it's just failing. System was busy with some of the workloads, but all of those different workloads have worked correctly at some point in time. This could still be a software bug. it could still be a software bug. It could also be a missing driver or feature that isn't doing certain of the, say, power management activities as it should. So the scope here is deliberately extremely wide, but there are two guiding principles to random failures, and that it is not a compiler bug until you can point to a specific bad app opcode and say why the compiler should not have omitted it. And even then, half the time, the people who report the compiler bugs are incorrect because they hadn't realized their code had undefined behavior in it. But nevertheless, the first step to being able to say the compiler hasn't done what I wanted is to be able to point to the bad opcode. And likewise, it is not a hardware bug until you have got fairly powerful evidence that you can give to your manager and that your managers can give the hardware team and you can use to leverage the involvement of the hardware team. Until you have got that evidence, I don't care if you think it's a hardware bug, you have to have some evidence to back up what you say. But there are some particular reasons why this is painful for kernel engineers. I'm aware we've hit time now. I'm sorry for that. This is a relatively short session, so we shouldn't overrun by too much. There's a reason that kernel developers tend to bump into this particular problem, and that is that kernel engineers are often exposed to weakly validated hardware. Especially for the commodity interfaces like USB, PCI, and Wi-Fi that are too complex for traditional validation by trying to stimulate the hardware and make it do something. There are likely to be bugs related to particular graphics cards that the validation department don't find. The final note is that the effect of SMP race conditions and memory corruption can be surprisingly difficult to distinguish, because an SMP race condition is usually a write to memory that doesn't happen when you thought it was going to. And that's much the same as memory changing state without it being memory changing state as a result of hardware behavior. So it's only something to bear in mind. It doesn't come up all that often. And the reason this is anticlimactic is because there aren't really any tricks. Nothing is going, no tool you're going to roll out is going to steer you towards this case much quicker than any other. That doesn't mean there is no advice we can offer. But we can't conceal the fact that ahead of whoever has got this problem is likely to be some significant work. So ahead of time, there are things we can do ahead of time to make things better for ourselves. Suggestions include things like kernel drivers or the bootloader should display every reset reason you can possibly find on your hardware. So part of random failure is random reset. Random reset, it's very helpful to know, was it a watchdog? Was it a thermal override? Was there a brownout? Was the what caused the device to actually go into reset in the first place? If you are working on a device with dynamic voltage and frequency scaling, that is one of the highest risk activities that a system can do, because we are basically, when we change the voltage, we are changing the way the power reservoirs in the system are going to behave, which means the risk of transient brownout is very exciting at that point. Frequency scaling, not so much, but it's the scaling of voltage. When we're changing power supplies, there can be wobbles on the power supplies, they change. There's lots and lots of things that have to happen very carefully to make voltage scaling possible. More than that, the nature of voltage and frequency scaling tends these days to be built on lookups in the chip. So there's a little table in the chip that describes how it was manufactured and allows you to tune the voltage and frequency scaling to match the sample. So it can get particularly convoluted in how these things work. So power supply changes are always some of the highest risk things that can happen. They should always be traced. You should have mechanisms with tracer points and understand how to use them to observe them. And they should be disableable. You should lock into particular modes. It doesn't mean that if you have disabled power management and everything works, that you can just hand it on to somebody else. I don't like the idea that by running, by disabling a bunch of features, you can then blame those features. That's not how it works. But they're still very useful data points to be able to say, when I turn this off, my random failure stops. It definitely allows you to come in, do more review of the software, more review of the, and so on and so forth. Having a P-store driver, this is the thing that backs up the RAM oops technology. Have one so that you can track oops and things like that and cover them easily. This is not entirely facetious. It says don't write SMP bugs. It basically means that there should be a sort of some kind of training program to ensure that your engineers understand both the interaction between SMP cores to some extent, to understand how to, ultimately spin locks will work. Clever lock-free programming requires you to know an enormous amount about SMP memory ordering. So the first level of training is use the real tool, use spin locks, use these other tools, pick things that have been reviewed by others. The second stage might be to learn how to write some of these things. Likewise, understanding the memory model, which we'll talk about in the very last slide, is important. So it sounds facetious, but it does imply that we need our engineers to have a particular level of understanding about how some of these things work. And finally, automation. Automation is a huge deal when things randomly fail, because what we really are likely to have to do is crunch statistics. We're going to have to get the failure reports. We find out the mean time between failure. We find out how often it manifests itself. If we don't know how often it manifests itself, we don't know if we fixed it or not, because we don't know how many tests we have to run to have any confidence in anything. So being able to automate the reproductions, being able to reboot and rerun when the problem manifests itself, so you can run overnight tests that give you more than one verdict overnight. Automation can make a big difference. On the other side, when the problem has actually occurred, first and foremost, good record keeping. So maintaining a summary of investigation. That's basically a counterbalance to a tendency to say, my board randomly failed, so I tried this, this. And when you hand that information to somebody else, they just get completely stuck. Well, why did you do that? That's just randomly kicking it to see what it does, which desperate people do. Desperate people certainly do. That's what turning off the power supply changes is an example of. But a good summary of the investigation means that you can describe the experiments that you've done, what you've ruled in, what you've ruled out, the leads that you have to work with. You should always retain all logs, all traces, anything that's been gathered as a memory dump, because at some point you might get a theory of failure, and rather than have to spend another couple of weeks reproducing the problem, you can go back to past memory dumps and do some checks within it. Once you have a random failure, you should always seek to replicate it on a different board, physically different board with a physically different power supply. Again, that doesn't always mean you can say it's not a problem anymore. If you've got samples with sample-specific tables to tell you how they manufactured it in them, the fact it reproduces on one sample and doesn't reproduce on the other doesn't mean you can just say the sample's broken. But at the same time, if you can show one board does work, one board doesn't, there is the possibility that board is actually physically broken, and you should then start, if you can see different behaviors between different boards, you then start doing a statistical project to find out if you can reproduce on anybody else's board. But once you've found 2 or 3 boards that all fail, then you start trying to work out what's common about them. But always, when you've got random failures, make sure the board isn't just physically deficient in some way. All the usual failure techniques still apply and should be deployed. So if the random failure may be to do with a quote random memory corruption, an overrun that's picking something unpredictably, you should definitely be running the fail early techniques to try and find it. At this point, you will start to be worried that the memory in the bus may not be working correctly. The memory might not always give us back what we stored in it, or more likely, the timings of the bus writing to the memory might actually result in lost bits every now and then when they're communicating with each other. Config mem test, the kernel boot time memory test, is not the right tool to tackle random failures. It's a useful sanity test, but if you are trying to tackle random failures and you're concerned that the memory reliability might not be there, always on memory tests running from either user space or from a coprocessor are typically a much better idea. And that gives you your smoking gun. If you're concerned that the memory is not reliable, it's not a hardware bug until you've proved it. And always on memory test is a really effective way to bring out a smoking gun. Although I can also offer you a war story that we had from the core dumps that we have mentioned next. We had managed to show that it really looked like an instruction had misfetched, because we could see that the instruction we just run, it was impossible for the registers to contain what they contained based on the instructions that preceded it. And the theory we had was that the iCache had misfetched. So we introduced always on memory tests. It was 3 weeks before we eventually got them to trigger. And then after that, it was very easy to get the hardware people in and get the memory retimed. but it was chasing that smoking gun was a 3-week process on many, many boards. So it still doesn't get you out of the woods necessarily straight away. And core dumps can be very, very useful if you are concerned that the hardware didn't act correctly. Unfortunately, a core dump on a platform with unreliable memory, you don't know whether it was the core dump that is misleading you or the problem manifests itself and caused the core dump to happen in the first place. But nevertheless, they can show you contradictions, but only if you've got them to fail early enough. And the final aside, before I go on to a few final closing remarks, is about memory barriers and I/O access. So just like lock-free programming is hard and spin-lock programming, well, spin-lock programming is hard and lock-free programming is harder. We also have a similar property here with accessors. So these are accessors to access memory mapped hardware. And these are relaxed accessors that do not contain the memory barriers. So ARM architecture has a weak memory model. What that means is the order that the core may write to some of its peripherals is not necessarily the same as the order they were written in by the executed in. And that's fine in most cases because within certain types of memory, ordering is preserved. So if you're talking to a particular peripheral and you do a write and a read, then it is guaranteed the write happens before the read, for example. However, if you're talking to two physically different peripherals, say, for example, a UART and a DMA controller that is paced by the UART, a write to one peripheral and a read to the other, the ordering is no longer guaranteed. They could happen any which way around. And readle and writle have got memory barriers in to prevent that from happening. Those memory barriers make readle and writle, by comparison, expensive. So people start to optimize by introducing these relaxed accessors instead, which is fine if they are well trained and are well aware of the nature of those relaxed accessors and how they can access and discover things. Additionally, even with memory barriers, that doesn't mean that a write has happened. When you do a write and a memory barrier and then some other stuff, that prevents reordering. It doesn't mean the write will have happened by the time you've executed memory barrier. It just means that nothing is going to move. So Will Deacon has a particularly good talk on this subject. It was at ELCE 2018. It's a good way to research things. But in essence, yes, if you see people using these accessors, particularly if DMA is involved, it is very, very important to recognize the orderings that can happen and double check that these APIs do what you think it's supposed to. So we're now heading into the wrap up and the free gift. So first off, I mean, Linaro Developer Services, I hope many of you have heard of Linaro before. Developer Services is the professional services wing at Linaro. It's where I work. And we provide the mixture of contracting, training, support, and potentially consultancy to people who are not Linaro members and to people who are Linaro members. We provide it to everybody, but it's a separate thing from the Linaro that some of you may know as the kind of industry consortium that is working to develop software for ARM. So developer services is a way for you to gain access to some of that knowledge that Linaro has on a professional services basis. The one that matters most to me, of course, is training. I'm the training manager. What you have been in today is a full module. We did not want to short sell people or do an abridgment or anything else. This is the full first module from our advanced kernel debugging course. And I mentioned, I think, the ftrace module, which is the second module. We've not got that coming up as a webinar, unfortunately. But yes, we have a great many courses. We have a catalogue online at the moment. It doesn't have any kind of registration or click-through. You can arrive on our website, linaro.org/services/hands-on-training, or just type Linaro training into a search engine. That will give you a training catalogue if you're interested in what we can do. My team is also responsible for technical support. So this is something we can add on top of any other contract to provide access to expert engineers to support anything that we've worked on previously. So we don't just do the work, we can stand up ticketed support behind it. And that gets us to the end of today's talk. So the free gift that I can offer you is a poster. The poster is basically almost all the buzzwords and techniques that I have mentioned during today's talk. There are a couple of bonus extras that I think we have read the material, so there will be one or two things like K-fence isn't on this poster, I think, at the moment. The idea behind this poster is that when you're staring into the abyss, when you're stuck, trying to remember what I said in a particular, because this is a really fast course, right? It's covering a lot of detail. We know it's covering a lot of detail. And something has to help you regain access to that knowledge when you're presented with a real bug. So the idea behind the poster is it's something you can stare at looking for ideas. You can see the clock neuron use. We have got KGDB and KDB in here. Perf is perhaps slightly oversized. It's not the most important tool in the debug arsenal. It's an important one, but it's not the most important one. But this is here just to go on the wall and help you find some ideas if you need them. And then finally, because this is our normal training module and we didn't want to sell anybody short, we have included all the lab sessions that we would normally include in our training. What I will mention, however, is that the stuff we are going to cover in the labs is only the things that we don't have other modules on. So there are certain things we introduce in kernel debug stories that we don't feel the need to train on anymore. Yeah, once you know about init calls debug, you can turn it on, you can run it, you know everything about it. There's no need for me to show you anything else. So this is all about studying those tools. If there was one thing you did in addition to these lab sessions, I would really recommend you spend some time trying to fire up ftrace to get that sense of what ftrace can do. As mentioned, I can talk for several hours on ftrace, but unfortunately I'm not going to. But I would recommend that anybody who wants to study these tools, ftrace is one of the tools that you come back to again and again and again. We've introduced what it's good at, but after working on the lab sessions, I would strongly recommend, if you can, spend a few minutes trying to get ftrace to run as well. We've provided a full kind of kit, software development kit, a VM, an image to play with, so that if you're sitting on an x86 machine, you don't have to have any ARM hardware to play with or anything like that. If you have your own system that you work in day in, day out, you know how to compile the kernel, most of the lab activities can be done on your own kernel. There's no need to use the kit we've provided, but if you want to use the kit we've provided, it's absolutely there for you to play with it. It's got some sneaky things built in. I think BPF trace is there to play with if you want to experiment with BPF. There's lots of, it's basically the development kit for a full kernel debugging course. So there's lots of bits and toys that you can play with if you're interested. And with that, I get to the end of all the material I wanted to talk about. Like I said, I'm sorry for the overrun. It is exactly the same amount of overrun as I had this morning, but I couldn't cover it any faster and expect you to keep track of what I'm saying. So I have done the very best I can to match speaking a little bit quickly, but not too quickly. I hope you've been able to keep up and I hope you've enjoyed it. I am going to just ad lib for maybe 10 seconds. So if there's any final questions, I will see them. I'm happy to spend the time talking about it. But otherwise, thank you very, very much for spending time with me. And I hope to see some or all of you when we're allowed out to conferences and wandering around again. Oh, that's an interesting point. Yes, QEMU and GDB. Yes, so QEMU has this lovely property that you can attach GDB to it. So we do actually have a course on symbolic debuggers where we just talk about stop the world debuggers. And yes, we do use QEMU and GDB as an example in that course because it has the same power as a JTAG debugger. So if you want to understand what a JTAG debugger can do, then QEMU plus GDB is essentially equivalent power. So if you want to find out what a JTAG debugger is great at, then use QEMU and GDB, and that can be a terrifically good way to see it. And of course, if you can reproduce the problems in QEMU, even better, you can use QEMU and GDB to study it, as Nick has mentioned. Thank you all very much indeed for spending time with me.